Hello everyone. Dean School of Engineering, Tezpur University is expected to join the meeting in a few moments. So we are waiting for him. After he joins, we'll start with the inauguration session.
Hello. Yeah. Hello everyone. I'm Shri Bhattacharjee, research scholar from the Department of Applied Sciences, Tezpur University. A very good morning to everyone present here. I would like to take this beautiful privilege to welcome our invited speakers, our guests, dear participants, and the chairpersons on this one-day astronomy workshop, Meet the IAU Astronomers, organized by the Department of Applied Sciences, Tezpur University, in association with the Office of Astronomy Outreach, International Astronomical Union. So now I would like to start our inaugural session by inviting Professor Rajiv Haloi, the head of the Department of Applied Sciences, Tezpur University, to deliver the welcome address. Thank you.
Yeah, good morning to all of you, and I welcome to this meet the IAU Astronomers. That is the outreach program actually supported by the International Astronomical Union, and this is the second program we are organizing. We have organized this type of program in 2022 also. So so I thank all the speakers for their valuable time. Dr. Sujatha, Dr. Sonali, Dr. Aruberi, Dr. Shama, for their consent to deliver a speech on this outreach program. And I hope all the participants of this event will enjoy their talk and will able to get some information and knowledge after the event. So I welcome you all to this event and hope this will be a grand success. So now over to Sri.
Thank you, sir. Now, I would like to invite Dr. Biplav Sharkar, convener of the workshop, to deliver his welcome address.
Uh, Hello, good morning, and a warm welcome to all of you. I thank our head, Professor Rajiv Haloi sir, for his encouraging words. I welcome Professor Parthopratim Sahu sir, Dean School of Engineering. I welcome all my colleagues and the resource persons, Dr. Sujatha Sriramalu, Dr. Shyama Narendranath, Dr. Sonali Sachdeva, and Dr. Aruberi. And most importantly, I warmly welcome the audience who have shown considerable interest in participating in this astronomy workshop. So today's workshop is the fourth event that Department of Applied Sciences is organizing. Tezpur University is very active in the field of astronomy and astrophysics. As Professor Haloi sir has already told, from the Department of Applied Sciences, this is the second astronomy related event we are organizing. Last year, we successfully organized our first conference related to high energy astrophysics. In the Department of Applied Sciences, Tezpur University, we have a small astronomy group of myself and my two research students, Ms. Sri and Mr. Arvind. So we work on the research area of theoretical modeling of astrophysical flows, the study of X-ray binaries, X-ray data analysis and interpretation. So today's workshop, Meet the IAU Astronomers, is being organized in collaboration with Office for Astronomy Outreach, International Astronomical Union. And I thank the Office for Astronomy Outreach for giving us the opportunity to organize the event. As you know, IAU was founded in 1919 and its mission is to promote and safeguard astronomy in all aspects, including research, communication, education, and development through international cooperation. The aim of today's workshop, Meet the IAU Astronomers, is to connect amateur astronomers, informal educators, and teachers with International Astronomical Union member astronomers through a virtual event. So through this meeting, the IAU members will speak with adults, educators, amateur astronomers, undergraduate, postgraduate, PhD students, and faculty members on astronomy topics and importance of astronomy for society and choosing astronomy as a career. The workshop today aims to enable the participants to meet professional astronomers and share the wonders of universe regardless of their geographical location. This program is designed so students and other participants can easily meet real astronomers. A very important aspect of today's event is the interactive session and career guidance for young aspirants by the resource persons who are distinguished IAU astronomers. I hope the audience will make full use of this opportunity. Although today's workshop is an online one-day event, in the future, we'll try to organize more such astronomy-related events on a larger scale. We are delighted that we have received a huge response with 662 registered participants in the workshop. Although we have a wide audience range, most of the participants are undergraduate and postgraduate students. We also have a high number of school students, PhD students, postdocs, faculty members, and other astronomy enthusiasts in the audience. So I welcome all of you again and thank you very much.
Thank you so much, sir, for your address. Now, I heartily welcome the Dean of the School of Engineering, Tezpur University, Professor Parthu Pratim Sharma, to convey his inaugural address.
Is it audible?
Yes, sir, you are audible.
Yeah.
Yes, yes.
So, kindly turn on your video.
Video is on actually, probably.
Okay.
Video is on.
Sir, we
Is
can
it
see
not
you
on?
now. We can see you.
Yes, sir.
Honorable experts, speakers, HOD Dr. Professor Rajiv Haloi, Dr. Biplav Sarkar. I'm seeing other member also online, other member of the Applied Science Department, and participants, students, and ladies and gentlemen. It is my great pleasure to be present in this workshop to deliver few words. Of course, the field is not my field. I'm not working on this field. Still, I'll say something about why astronomy is very, very important. Subject of astronomy is very, very important. Little bit, not much. I don't have idea, of course. And experts knows better than me. Expert, I mean other participant also better than me. I know a few scientists who is working. I know Professor Nadikar. I attended his lecture in IIT Kharagpur. Professor Rana, he belongs to my place. I know personally. He's one of the brilliant guys. He expired at a very young age. He could not do much. I know even our university, there are a lot of activity. We have an astronomical club in our campus, and there are a lot to know about the objects, different objects outside the Earth, maybe star, maybe other objects which situated. We have to know all these things. Otherwise, it will be very difficult to sustain our life on the Earth. We'll see. The matter of fact, the Earth is so, congested now with the human. Even after maybe 100 years, we have to think about to our existence in other planet or other places in the Earth. Maybe people are thinking about that. There are a lot of missions going on in this direction. Different countries doing. Our ISRO, in the Swiss Research Organization, they are doing. I've seen some of the lectures delivered by our by ISRO scientist, probably Dr. Sama Narendranath is delivering lecture about the moon. We have to think about the how we can life can sustain in the other planet. We have to see, we have to search the water, oxygen, which is very important fundamental component required for the existence of life. That is, these two components has to be there. So if we can search the object and we can see the existence, our existence in other planet also. Not only that, we have a lot of, a lot of metals, lot of materials, which is very important for carrying out for smooth life, like maybe earth, maybe gold or other metals, which is precious metal, maybe there in the other astronomy. So we have to search for that. Astronomy is one of the area which can uh, enlighten us, and not only that, the climate change, all these things are happening on the earth. We have to see how the astronomy linked to this climate changes, all these things. So I'm not tell much because they're expert, they can tell. And formally, I inaugurate this uh, seminar or workshop, called a seminar, meet the IAU astronomers. So with this, I conclude here, and I hope that the participants, students or learners, they know more about the astronomy. What are the area we should focus on the astronomy, and it will be benefited to all of you. Thank you very much inviting me, and formally we invite this workshop. Thank you.
Thank you so much, sir. Now, I would like to invite Professor Dhrubajyoti Haloi, Assistant Professor of Chemistry from the Department of Applied Sciences, Tezpur University.
Just let me know first whether I am audible or not. Am I audible?
Yes, sir, you are audible, but a bit volume is a bit low.
Maybe about the volume I am not able to find.
Okay, sir, please go ahead.
Sorry.
Please go ahead, sir.
Okay. Very good morning to you all present in this virtual room. Respected teacher and our respected astronomers, come speakers of today's online astronomy workshop, which is Meet the IAU Astronomer 2023. Dear participants, my dear colleagues, friends, and students. Though already Professor Rajiv Vallabhi, head of the department, already welcomed you, and Biplab Chowkar, as well as our dean sir also welcomed you. I also like to welcome you on behalf of the Department of Applied Sciences to this virtual workshop. So, as already mentioned by Biplab Chowkar, this is the second workshop of this kind organized by Department of Applied Sciences. The previous was organized in 2022. The Department of Applied Sciences was established in 2019 under the School of Engineering. The first batch of faculty joined in 2020. Dr. Biplab Chowkar, who is the convener of this workshop, is one of them. So at present, we are having 7 faculty members in our department, physics, chemistry, and mathematics background. We also have 16 number of PhD students who are being engaged in research being under the School of Engineering, our main responsibility is to take care of the engineering students, provide them with a strong foundation in applied sciences. At the same time, we are also trying to expand. We are also focusing on research aiming to be enter the frontier areas of applied sciences. And of course, to be tuned in the latest scientific findings, development, information and technology. This kind of workshop or maybe the conference or scientific meets are very much essential. So I feel and I believe that the IAU Astronomer 2020 is one such workshop. And I do hope through this meeting, the participants will be able to know the latest findings and progress already made in the astronomy and astrophysics field. This workshop also will give the participant an opportunity to interact with the astronomers directly to exchange their views and ideas. At the same time, I would like to thank the speakers for accepting our invitation to be part of this workshop. They are going to deliver their speech very soon. And I also thank the participants and the other members of this particular workshop for showing their interest in being with us. In fact, they have already joined with us. I would like to thank Dean sir and thank to the department for their encouragement to organize such an event, for their all-time support. At last, I appeal to you all for your active participation to make this workshop again a success. Thank you.
Thank you very much, sir, and thank you to everyone for their heartwarming addresses. Now, please allow me to Now, please allow me the opportunity to briefly highlight the activities of the workshop. So, there will be two sessions in this workshop, the morning and the afternoon, including two talks in each session. The speaker of the first sessions are Dr. Sujata Sriramulu from MP Birla Institute of Fundamental Research, Bangalore, and Dr. Shama Narendranath from ISRO, Bangalore. And the speakers from the second sessions are Dr. Sonali Sachdeva from RRI, Bangalore, and Dr. Aruveri Isomithil. Now, with this, let us conclude the inaugural session here. Now, I would like to invite Dr. Vijay Krishna Devnath to chair the session 1. Thank you.
Thank you, Dr. Shoykar, for giving me this opportunity to chair the session. Am I audible to all of you?
Yes, you are audible.
Okay. So, I welcome both the speaker of this first session, Dr. Sujata Sriramulu and Dr. Shema Narendranath. Let me introduce the first speaker with you all. Dr. Sujata Sriramulu, ma'am, is a scientific officer at MP Birla Institute of Fundamental Research, Bangalore, and she completed her MSc in Physics from Bangalore University and PhD in Astrophysics from Bangalore University. She has guided short-term MPhil research students, MSc and BE project students. Also, she is a member. She has membership in several professional organizations. Like she is an active member of the International Astronomical Union and also a life member of the Astronomical Society of India and Indian Physics Association. Her research area includes, not limited to, the photometry of open clusters and spectroscopy of epistars. She is also interested in the history and philosophy of astronomy education, communicating astronomy with the public, astronomy outreach, and astronomy for development. Today, she will deliver her talk on astronomy for all, a citizen science approach. So, with this, I would like to welcome you, ma'am. Please deliver your lecture.
Yeah, thank you, Dr. Vijay. Am I audible?
Yes, you are audible.
Just turn on my video. So, can I start sharing my screen? Is it okay?
Yes, sure.
Yeah. Okay. Yeah, can you see the full screen now?
Yes, ma'am, it will be better if you can make it slideshow.
Slideshow.
Then the page will be pop up, right? That means there is one button in this.
Just a minute.
It was okay as it was earlier. How you open this, just the same procedure. Only you have to open the that means slideshow mode.
Just a minute, just a minute. I'll just stop sharing and then maybe here I'll be able to do it. Okay, share a window. Just I think the share screen option is missing for me right now. I'm not able to see that. Oh yeah, now it's fine. Now it's fine. Now it's fine. Yeah.
Okay.
What is it? Again, it's gone.
Ma'am, can you log out and log in again?
Yeah. Yeah, can you see me now?
Yes, we can see you.
Yeah, let me try sharing now. Not able to. If I do my entire screen, then it's not showing me to. Okay, let me see. I'll try with the entire screen.
Yes, yes.
Yeah, is this better?
Yes, better.
Yeah, is it clear now?
Yeah, ma'am, can you hide that one?
Now it is
Stop
okay.
sharing and the hide option. Yeah,
Yes. Done?
yeah, ma'am. It's perfect.
It's perfect? Okay, good. So can I start?
Yes.
Should my video be on or can I switch off the video because it might save some bandwidth?
Yes, sure. You may switch off your video.
Yeah, I think it's okay. Let me just continue and will not stop. Thank you, Dr. Biplab and the entire team for organizing this program, which is Meet the IAU Astronomers. And I'm privileged to be here to be giving a talk to you all. I heard that there are almost 600 participants here, and most of them are UG and PG students. But I assume that not all of them have astronomy background. So I have designed my talk in such a way that the talk is very basic, simple, and easy to understand. There are two components of this particular talk. I'm going to give you a brief of the astronomy, the basic principles that is required for anyone to carry out astronomy as a hobby or even as a professional astronomy. Okay, and with these basics, how is that you can contribute towards astronomy as a citizen. You don't have to be a professional astronomer, or you don't have to be an amateur astronomer as well. You might be a computer professional who would just like to contribute towards data. Astronomy is a subject where there is so much of data available, and we want human touch to understand this particular huge amount of data. So even if you're a computer professional who like to contribute in terms of data analysis, you can still contribute. So how one can give their contribution to astronomy is this concept of citizen science. Okay, so citizen science, it's not limited to only to astronomy. It is there in almost all fields of science, not only science, even in arts and in humanities and many other fields as well. The citizen contributions have been asked for. Okay, so in this particular small picture, you can see where are the fields where the citizens, normal citizens, can contribute to. All that you need is a little bit of interest, and then a little bit of time, and your computational time that is required to contribute here. So in this particular picture, what you see is one of them is, of course, depicting the night sky with a lot of shiny objects around there. And then on one side, you see this butterflies. So even categorizing the butterflies is part of the citizen science. This butterfly community is really huge, and classifying the butterflies, various types of butterflies that is available on the earth itself, is a huge task. So that's also a part of citizen science. And even categorizing the microorganisms. There are a lot of projects even in categorizing the microorganisms, even the bird classification, classifying the birds, and even identifying some of the birds which are almost extinct, and trying to preserve our natural beings around. Okay, so citizen science, it's not limited to astronomy. It is applicable to various parts of science and various parts of humanities as well. However, today I'll be concentrating only on astronomy and astrophysics, how one can contribute towards this particular field. So when we look at the universe, and if one would like to give your address, suppose let's say that we are progressing so much that we have found our counterparts in some other galaxy, and if you would like to give your address to the counterparts in your other galaxy, how we would give our cosmic address is, you start with your street, city, state, country, and then you would start going to the continent, which continent we belong to, which hemisphere, which planet, and then which orbit, and to which star we belong to, going further to which galaxy we belong to, and then the question goes on. So where does this end? Initially, we thought that everything is only the Earth. There's nothing beyond the Earth. This is, I'm talking about when humans started wondering about the sky, not currently. Now we know that the universe is huge and there are many objects around us. All right, so now let's look at our position in this kind of cosmic address. So we all start from this, currently we know that we all belong to this group of galaxies called as the local supercluster. And this local supercluster is itself a part of the local group of galaxies, which means that our Milky Way galaxy itself is a part of the local group of galaxies, within which even Andromeda galaxy is part of our local group of galaxies. Now, within Milky Way galaxy, we belong to a system called as the solar system. Now, within solar system, we belong to a planet, or the third rock from the sun, which is called as the Earth, and we live on Earth. So our analysis starts from our immediate surroundings, that is the Earth. Earth is the rocky planet which is available to us immediately, and this particular rocky planet, the more we study, it is not enough. there are still a lot of questions remaining about the Earth itself, and including the kind of species that is available on the Earth. These studies itself is totally incomplete. There is lots and lots of more things that we need to study about Earth, especially the living beings on the Earth. But looking at the astronomical perspective, we look beyond the Earth, and beyond the Earth is the first star that we encounter from the Earth is our Sun. Sun is the nearest star to the Earth, and wherein you get many the whole life itself is possible because of the Sun. Probably if the Sun was not there at that particular right distance, even we wouldn't have existed. The Sun and the Earth are so nicely placed at the right distance that the evolution of life itself could happen. So we need to be thankful for the Sun. But is this relationship between the Sun and the Earth going to be continuous? Is this permanent? We all know that it is not permanent. The main reason being the Sun itself is a star, and we know that these stars do not live long. I mean, astronomically speaking, they don't have endless lifetime. They don't live in the same form throughout their life. They have their lifetime, and as of now, the Sun itself, we know that it's a middle-aged star. It's about 4.5 to 5 billion years old, and it will live for another 5 billion years. So what would happen to the Sun-Earth system after this? Okay, it's a question mark. And if we have to move out, if our so-called Homo sapiens have to move out of the Earth, where else can we go beyond this particular solar system? So these are some of the questions which has really pushed the astronomers to look beyond the Earth. So once we started looking beyond the Earth, we first started looking at the solar system planets. Solar system planets is, we look at our neighbors, that is Venus, and as well as Mars. We know that Venus is not habitable because its atmosphere is very thick and rich with carbon dioxide, and there's too much of greenhouse effect, and it is not really habitable for humans. So what we do is the next planet where we can probably shift to is Mars. And Mars has its own dangers around Mars. That's because the atmosphere of Mars is very, very thin or almost negligible. Right now, we are safe on the Earth because of the atmosphere of the Earth itself. It protects us even from the harmful radiation that is coming out of the Sun. So next is we would like to look deeper into the solar system. So in our solar system, we all know that there are 8 planets or 9 planets. I would always go with 9 planets because right from my high school times, I've been taught that Pluto is part of the solar system. We have read it as the solar system consists of Sun and 9 planets. So it's very hard for me to demote Pluto as a planet because it is seated very deep into my mind that Pluto is part of the solar system. But IAU, there was a voting happening, and there was redefinition of planets by redefining what can be classified as a planet and which object cannot be classified as a planet. In such kind of redefinition, Pluto was actually demoted as a planet. So right now we have 8 planets that comes under the solar system, and Pluto and the objects which are beyond that, we simply call them as dwarf planets or give different kind of definitions for them. So when we consider the solar system objects, you have the planets, and between the orbits of the Mars and Jupiter, you have huge pieces of rocks that is being circulating in that particular orbit, which we call as asteroids. Asteroids are also integral part of the solar system. And if you go beyond the Uranus and Neptune orbits, you have the Kuiper belt, and beyond that you have the Oort cloud, which Oort cloud is a kind of, we can say that it's the edge of the solar system. We do get once in a while visitors to the Earth from the Kuiper belt or the Oort cloud, which we call them as the comets. So in a nutshell, our solar system consists of the sun, planets, asteroid belt, and once in a while visitors, the rocky bodies, which are the comets. So these are the kind of objects that we have within the solar system. But are all these objects really habitable? Can we live without the sun? Or are there any exoplanets, that is the solar system beyond our own solar system, which we simply call it as exoplanetary system? So if we need to have or look for such a place, then we need to go beyond our solar system, which we simply call it as the solar neighborhood. Okay, so solar neighborhood is something like, you can say, about 20 light years radius, and look around the solar system. Within the 20 light years radius, what are the objects that we can find? What are the stars? And do these stars have planets like our Earth going around them? If there are planets like Earth, are they habitable? Can we live there? So this is one of the questions. There are many more questions to be answered, but this is just one of the questions. So we expand our horizon to the solar neighborhood, trying to look at the objects which are in the neighborhood of our solar system itself. And we are not happy with that. It's not enough for us. We would like to proceed further and try to look at what is our position within this particular universe. So when we try to answer that question, what is our position, that is, what is the position of the solar system with reference to the neighbors, then that's when we get a picture of our galaxy. Okay, so our galaxy is the Milky Way galaxy. Now we know that we are part of the Milky Way galaxy, and we also are very certain that we are not at the center of the galaxy, we are at the edge of the galaxy. We are along the one of the arms of the Milky Way galaxy, and we are actually like almost at the edge of the Milky Way. We are out of the Milky Way, outskirts of the Milky Way galaxy. Okay, but fine then. So is the Milky Way galaxy the only galaxy that we have in our universe? The obvious answer is no. Even with the naked eye, we can see the only spiral galaxy that is visible to the naked eye is the Andromeda galaxy. So closer to Milky Way galaxy, the spiral galaxy that we can see even with the unaided eye is the Andromeda galaxy. There are LMC and SMC, that is Large and Small Magellanic Clouds as well, that is visible to the unaided eye. But you need to go to the southern hemisphere, that is, you need to go to Australia or New Zealand or even to Mauritius. Any place below the 0 latitude of the Earth, you will be able to see here. Below the equator, you will be able to see Large Magellanic Cloud and the Small Magellanic Cloud with the unaided eye. All of these form the local group, that is Andromeda, LMC, SMC, and many other small galaxies, including the Sagittarius dwarf galaxy. They're all local group of galaxies which are actually gravitationally bound to each other. This is the local group of galaxies. So starting from the Earth, we have seen that the universe is, when we try to look deeper and deeper into the universe, we see that we are not just part of a solar system. We are not even part of a galaxy. We are actually part of a local group of galaxies. It doesn't end there. So do these local group of galaxies belong to something else? Yes, they do belong to the local super cluster of galaxies. So there are local group of galaxies. All of these things form another super cluster of galaxies. So now you can imagine how many such galaxies could be there in our universe. Okay, so this is whatever I'm talking about. It is talking about only around our own galaxy. Okay, that is a Milky Way galaxy, local group of galaxies, and super clusters of galaxies. Now look at the structure of the universe. How many such super clusters of galaxies are there? Okay, so this is going much, much deeper into the space. This is where our telescopes, space telescopes like Hubble Space Telescope was really helpful in understanding the observable universe that we have. And now we have JWST. So later in the part of the lectures, you will be understanding about what are the discoveries done by what is the science done by JWST telescope. These telescopes, space telescopes, really helps us to understand the deeper sky, and also it helps us to understand the structure of our universe. Okay, so now once we can only stop at universe right now, because we do not know what is beyond this universe. Okay, so imagination wise, one can say that, yeah, it doesn't end at universe. Uni means one. There can be multiverse. There can be many universes. There can be parallel universes. There are many such things. But here I'm going to limit it only to what is observable, and for what we have the scientific proofs, and which is well set kind of results. So what you're seeing right now on the screen, it is all these structures. What you see, it's called as a filament structure, or the web kind of structure, and it looks like a spider web. And in this spider web kind of structure, you see here each blob, what you see, the orangish or reddish kind of blobs, what you see, they are all these local super clusters of galaxies. And these super clusters of galaxies are connected with each other, and which looks like a cosmic web. We simply call it as the cosmic web. So this is the kind of understanding we have in a hand-waving kind of explanation about our universe, the observable universe. Okay, so I'm not talking about any theoretical perspective here. It's the observation point of view. Okay, so this is the filament structure of our universe, the observed part, and whatever the results is being really set. Now, having been talking about these things, how do we know so much about the universe, about our position in the universe? For this, there has been development in the astronomy and astrophysics, the observations, as well as theoretical concepts. Everything has come together, and then we try to answer these questions. So one of the basic things that one has to know about these objects in the sky are, there are basically 4 parameters one has to know. The luminosity or brightness of the object that you're studying, it can be an individual star, or it could be even a galaxy. For these objects, we need to study about their size, their mass, their surface temperature, because these are the ones which tell you about these objects' past, the present, and their future. So these are very necessary concepts that one has to know. And to know these concepts, one should also know the distances to these various objects. Now, in my slides, you would have seen that when I was talking about the solar system, especially within the sun and the distances to the solar system objects, something called AU was written. AU stands for astronomical unit. Okay, and also I have used a term called light years. Light years is yet another unit which can be used for representing the distances to various objects. Now, what you see here right now on the screen, it's a very famous constellation called as the Orion, the Hunter. And in Orion, we see these 3 stars, which stands as which is represented as a belt of the hunter. If you go to the mythological stories, you would know that somebody had imagined this Orion constellation to be as a hunter, And these three stars, which are in a line, it is called as the belt of the hunter. And somewhere below the belt, somewhere around this particular region, it is the sword region or the dagger region, and in that particular region you have the nebula called as the Orion Nebula, which is the kitchen of star formation. It's the place where the cooking of stars take place. So we also look at the star formation, how they are forming. Now coming back to these three stars in the Orion constellation, these three stars to us from the Earth, they all look as if they are in a straight line, and it appears that they are all of equal illumination, and it gives us a feeling that okay, they all might be at the same distance. Okay, but in reality, the fact is not all the three stars are in the same state of their life. Not all of them are at the same distance. Now in the same frame, you can see here yet another star which is called as Sirius. Sirius is the brightest star for the northern hemisphere people. Even now, probably here in the east, you would be able to see this star Sirius, which is the brightest star in the night sky. Okay, so although Sirius appears to be as a very bright object, it could be bright to us because it is extremely close to us. Extremely in the sense it is closer to us compared to these three stars in the Orion belt. So now how do we compare these things based on their appearances? So how do we know that how far each of these objects are present? Okay. And now another nice thing about this particular part of the sky is Orion is the hunter, and this hunter is followed by this particular constellation which is called as the Canis Major. Okay, Canis Major, Canis means it's a dog, Major means big dog. So Sirius belongs to this particular constellation called Canis Major. It's a very prominent constellation during the winter sky, starting from November to maybe up to end of March or even mid of April. Around this period, you can see these two constellations somewhere in the western sky immediately after the sunset. Okay. So now we'll just quickly go through the distance scales and where we use what kind of distance scales. So we have already talked about the astronomical unit, and the other unit that we use in astronomy is light years. And then the third unit that we use is parsec. Okay. So astronomical unit, it's a unit which is nothing but it's defined as a mean distance between the sun and the earth. It's a unit which is used only for objects within the solar system. Beyond the solar system, we do not use this unit, astronomical unit. So whenever something is represented in terms of AU, it means that we are talking in for the objects within the solar system. The next unit is a light year. We all might be already knowing that light year is a measurement of distance. It's nothing but the amount a light can travel in one full year at the speed of 3 × 10⁸ meter per second. In terms of kilometers, it's 9.45 × 10⁻15 meters or something. It's a huge number. Okay, but even though light year is a unit which is used as representing the distances, it's not a unit where we can really measure. Okay, all that you know is when we have received the light, but we do not know when the light has left an object. Now, suppose if I say that Proxima Centauri is like 4.3 light years away, or approximately. Okay. So how do we know that Proxima Centauri is 4.3 light years away? Is there any measurement that we have done using the light there in terms of light year? It is not possible. Okay. All that we know is we have only received the light today. We do not know when the same light has left that particular object, at what time and when the light has left that particular object. During its travel, it has spent some amount of time and then it has reached us. Even for the sun, we say that the sun is 8 light minutes away, which means that the light has taken 8 minutes to reach from the sun's surface to the earth, to us. It takes about 8 light minutes. Okay, but how do we exactly know when the sun, when the light has left the sun, when the photon has left the surface of the sun? Okay, so light year is not a kind of a measurable kind of quantity. What astronomers do is they actually measure the distances in terms of parsec. Parsec is nothing but it's an abbreviation of parallax second, and usually it is an angular measurement. We measure the angle subtended by an object with reference to the orbit of the earth around the sun. Okay, so in this particular picture you can see it is just a triangulation kind of thing. This particular angle is called as the parallax angle. When earth is at this position around the sun in the month of January, from this position you are trying to look at a nearby star with reference to the background objects. But the same object, okay, same celestial object, 6 months later, the Earth's position would have shifted around the sun to a different location. The same object which we are looking at in the month of January, it would be appearing as if it has shifted its position in the sky with reference to the background objects. In reality, the object has not shifted its position, but the Earth's position has relatively changed in these 6 months. So if you try to measure that angular shift within those 6 months, this angle, which we call as the parallax angle P, gives us the distance to the stars, which we use a simple relation of D is equal to 1 over P. That is, it is inversely proportional to the parallax angle. If the parallax angle that you measure is a smaller angle, then the distance is very, very far. Okay, so this is just one of the methods to get the distances to the stars. Actually, the term called parsec for the distance measurement of celestial bodies was derived from this kind of heliocentric parallax method. So I just showed this method only to show you to understand this parallax method. But this is not the only way to measure the distances to the objects in the sky. There are many more methods. There are drawbacks for this particular method. So there are many other methods which can be used to measure the distances to the objects in terms of parsec. So once the distances are measured in terms of parsec, then it is converted into light years. We have a relationship between the light years and parsec, where 1 parsec is equal to 3.26 light years. There's a beautiful derivation for all of these things, but if you're interested, you can just look up how to convert 1 parsec to light years. Okay, so 1 parsec is nothing but 3.26 light years. So that's how this term called parsec has come, and that's how we know how to represent the distances for the celestial objects in terms of parsec. So again, in a nutshell, for the distances within solar system, we always use the term AU for the distance measurements. Beyond the solar system, we measure the distances in terms of parsec and then convert it into light years. Okay, using the relation 1 parsec is equal to 3.26 light years. Now, once we do, there are some drawbacks in the parallax method to measure the parallax angle. So we need to resort to different methods of measuring the distances. So for that, we need to depend on the light that we receive from the objects itself. Light that we receive, it can be from the galaxy, it can be from the stars. Okay, so right now I'm going to limit myself only to the visible spectrum of light. Visible spectrum is only from the red wavelength to the blue wavelength, but we do measure, we do receive light in different wavelengths. It can be in X-rays, gamma rays, it can be infrared, it can be even in radio waves. Okay, so that's where the whole radio astronomy has developed, where you measure the light received in terms of the radio wavelength. But whatever it is, the principle of these brightness remains the same. So the term called magnitudes, or something which is related to brightness, it is first developed by Hipparchus, and he had classified the stars into 6 groups. Okay, so the brightest that he could see with his unaided eye, he called it as magnitude 1 stars, and the faintest that he could identify, we call it as the 6th magnitude star. In between, you have 1, 2, 3, 4, 5, 6. Okay, so ideally speaking, on a clear, dark sky and with good eyesight, we should be able to see up to the 6th magnitude star. For example, our Polaris, it is about, it's a variable star. Its magnitude can vary. And Polaris magnitude, it's around 3 magnitude. Okay, so in our polluted sky like our Bangalore, we can probably see up to 2nd magnitude star or the 3rd magnitude star maximum. Okay, but if you're in the remote areas, probably in Assam, I presume that it is not encroached with too much of light pollution. There probably you would be able to see even up to the 6th magnitude star. So magnitudes, it's nothing but it's a representation of the brightness, where the lower number represents the brighter objects, and the higher number represents the objects which are fainter. It was first introduced by Hipparchus. That Hipparchus had introduced it with reference to what our eye could perceive. Okay, but later on, when the instruments were developed with the telescopes and with binoculars, when you can actually measure the light energy, using these instruments, we have redefined these brightness of objects. We simply classify them as 2 things. One is the apparent brightness and the other is the absolute brightness. So apparent brightness is nothing but it is the brightness of an object as it appears to the instrument. Okay, even in this case, the apparent brightness, it based on the amount of light energy that you receive, the classification is based as it can go from negative value to the positive value. And this kind of reclassification of magnitude system happened because of the introduction of instruments where you can probe deeper into the sky and you could start measuring the light energy with proper instruments. Okay, and for obvious reasons, sun being very close to us, the sun's apparent magnitude turns out to be as minus 27. And the next brightest object that we can see in the sky is the full moon. Full moon, when it is there, its apparent brightness, it's called as minus 13. So all that I want you to grasp here is, if you take a star catalog, and in the star catalog, if the magnitude system is given, the magnitude system is always represented in terms of the apparent magnitude, which means that if the star catalog shows the number as +6, then it means that that particular object should be visible to you with your unaided eye. You don't need a binocular or a telescope to look at that particular object. Okay, so here Sirius is bright, which is apparent magnitude is minus 1.4. So I hope this particular concept of apparent magnitude is clear. But now the question rises, okay, then how do we compare these two, any 2 objects in the sky? Okay, so Sirius is minus 1.4, Sun is minus 27 in terms of their brightnesses. And they are bright because one object is close, one object is far. But then how do we really compare them? Is Sun is brighter or is Sirius brighter? Okay, so when you compare these 2 magnitude system, these 2 objects, for comparison purpose, we define another magnitude which is called as the absolute magnitude. It's nothing but it's a magnitude of an object or the brightness of an object if the object is placed at a distance of 10 parsec. So, sun is very close to us. Okay, it is only at a distance of 1 astronomical unit. You push the sun to a distance of 10 parsec. Okay, so intuitively you can say that if something which is bright, which is when it is close to you, if you push that object farther, it would obviously look fainter. Okay, something which is very far away, if you bring that particular object closer to you, then obviously it would look brighter. So here you're trying to compare their brightnesses. All right. So what would happen is sun is shifted farther, Sirius is brought closer, and now on this particular distance scale of 10 parsec, you're comparing their brightness. So that brightness is what we call as the absolute magnitude. Okay, so just to give you a feel, if sun, which is so bright because of its proximity to us, if you shift sun to a distance of 10 parsecs away, the sun's brightness would go close to 5th magnitude, which means that definitely for me, who sits in Bangalore with so much of light pollution, sun would definitely not be visible for me at its absolute magnitude scale. Okay, so it is just basically a way to compare two objects, the brightnesses with apparent and absolute magnitudes. So here is just a scale to show you the comparison between apparent and absolute. And there is, once you understand these concepts, there is a beautiful relation between apparent magnitude, absolute magnitude, and the distance. Okay, so in astronomy, there are ways where we can obtain this apparent and absolute magnitudes by plotting various diagrams and using some theoretical models. Once we get this modulus, that is the apparent and absolute magnitude modulus, we can actually calculate the distances to the objects. So it's not necessary that one has to have only the parallax angle to measure the distances of the object. We can use their brightness itself, measure the brightness itself, and then try to estimate the distance. So once you estimate the distance in terms of parsec, you can convert them into light years. So most of the popular science books, we don't show the results in terms of parsec. The results are shown in terms of light years. It's mainly it's much easier for public to understand in terms of light years than in terms of parsec. But whatever we do in astronomy, our techniques, our results are also always in terms of parsec, and then we convert it into light years. Okay, so here coming back to our Canis Major constellation, what you see on the left-hand side, Sirius, which belongs to the Canis Major constellation, this is how it would look like to our unaided eye. But if you place all these stars at 10 parsec distance, all the stars that you can see on in the direction of Sirius, in the direction of Canis Major constellation, if we estimate all of their absolute magnitude, and if you put them on this graph, now you can see that see the comparison of this particular star Sirius with reference to the other stars in the constellation. So absolute magnitude is a term which gives us an understanding of the real brightness of an object in comparison to the other objects in the neighborhood. Okay. So that's about the magnitudes or the brightnesses about the objects. The very most important, yet another important parameter of the stars that one can estimate or one needs to estimate is their surface temperatures. Okay, so if you have noticed the colors of the stars in the sky, the stars can appear reddish, orangish, yellowish. Okay, and there are blue stars as well. All right, but most stars appear white in color. Okay, so what do these colors actually mean? The colors actually indicate their surface temperatures. The surface temperatures indirectly it could indicate what is happening inside the stars as well. Okay, so the surface temperature, based on the surface temperatures of the stars are classified into various groups, they're called as O, B, A, F, G, K, and M type of stars. O type stars are the hottest type of stars. Now here in this particular diagram, which we call as the HR diagram, I'm showing you here what are the different types of colors of the stars. You have O type, B type, A, F, G, K, and M type stars. They are the spectral classification of stars based on their surface temperatures. Now, how do we get the surface temperatures? It's only by analyzing the spectrum of the stars. How do we get the spectra? Again, just as you use a prism and a spectrometer to split the white light, and then you try to analyze the spectra in your lab, similar thing is done with the stars as well. The star light is subjected to an instrument called as a grating or a grism, or there are various instruments which can be used, and those instruments are used to actually get the spectral classification of the stars. We can try to analyze what type of star it is. Is it a hot star or is it a cool star? And also, it's not only that. Now you can see here in this particular picture, there are some dark lines shown. Dark lines talk about the absorption features. Absorption features means at those particular wavelength, there are certain elements present inside the star, and we can also analyze what are the elements that are present inside the star, and depending on the abundance of that element, how much of that element is present, that also can be done using the spectra of the stars. Now, this is a very simple diagram. It's called as a diagram, but basically it is a graph called as a HR diagram. For any astronomer, be it a professional or amateur or a beginner, whoever it is, they should know what this HR diagram is. HR diagram, it's nothing but it's a plot of anything related to brightness with reference to their spectral class or temperature. Okay, so on the y-axis, we plot anything related to the brightness. It can be magnitude, it can be luminosity, anything related to the brightness of the object. And on the x-axis, we plot the temperature. Okay, so when you plot, what we see is most of the stars, they lie in this particular band, which is called as a main sequence band. Now, in the main sequence band, what we can understand is these are the stars which are still having hydrogen at their core and burning, which means that they are still in their living stage. Once the hydrogen at the core of the stars is over, that's when they start behaving differently. Their surface features would change. If a star is bluish on the HR diagram, once the hydrogen fuel is over, it would go towards this right-hand top side of the HR diagram, which means that their features are changing. Okay, it can become cooler, and cooler means it should look reddish in color, and the star can become luminous. Okay, all these things can happen because of the processes that's happening inside a star, which is part of the stellar evolution. Now, right now, due to lack of time, I cannot explain all of that, but I want you to understand this HR diagram, various parts of the HR diagram. Mainly, you have the main sequence, you have the giant branch, and you have the white dwarf branch. Okay, so any astronomer, observational astronomer, if they are studying the individual stars within the galaxy, or if they are studying the groups of stars, we try to locate their position on the HR diagram. By looking at its position on the HR diagram, we will be able to tell in what stage of life this particular object is in. Is it in its living stage, or is it in a protostar stage, or is it an evolved star, or has it become a white dwarf? Okay, so those are the things that we can derive from these basic concepts. So the basic concepts that we have so far seen is you have the distance scales, you have the magnitudes which are apparent and absolute magnitude scales, the temperatures of the stars, and all these things can be plotted on a HR diagram. And using the HR diagram, you can talk about what is the current state of that particular object. Now, we have seen all of these concepts, and we have also gone through a quick tour of our position in the universe, in our surroundings. So based on your interest, you can contribute to the astronomy community. There are a lot of already available data, archival data available online. And this archival data, it's not limited only to galaxies or to minor planets or only to one or two planets. None of those things. It's available for the entire spectrum. Okay, so entire spectrum, entire wavelength spectrum. If one is interested only in solar physics, there are sites where you can look into for solar physics, where you can get the data and then start analyzing on the solar data. And similarly for astrobiology, planetary science, minor planet study, and all these details. Okay, so I'll just show you a few of the places where you can find the data and how your contribution could help. Okay, so who can contribute towards astronomy is with the available data and with whatever background knowledge you have. Is it can be general public. There is no necessity of any background education. All that you need is the interest. Anybody can contribute for this these particular projects. One of the most famous projects that is available is on zooniverse.org. You can just log into the Zooniverse. You can just look up as Zooniverse, and you can look for the projects under astronomy. Zooniverse, one of the famous projects under Zooniverse is classification of galaxies. Galaxies, they come in various shapes. Spiral galaxy, it can be elliptical galaxy. In spiral galaxy, what type of spiral it is? Okay, is it a barred spiral or it's a simple spiral? So those kind of classification is done. And even though we have AI in this particular field, still nothing like a human touch. So this is where the humans also contribute, and there is enormous amount of data which keeps on being released on the zooniverse.org. You can look for projects under Zooniverse and then contribute accordingly. Okay, and there is yet another site called as Einstein at Home. At home sites are there. One is Einstein at Home, and then Milky Way at Home. In India we have the RAD at Home. Okay, so you might have heard about it. It's dedicated to radio astronomy. That's why it's called as RAD at Home. Okay, and Milky Way at Home, it's a very interesting project. We always assume that Milky Way is a spiral galaxy. Okay, but who has seen Milky Way from outside? It's so hard to get out of the Earth itself. It's so hard to go up to Mars, so go up to Moon, and then take the picture of the Earth. But who has gone out of the Milky Way and taken the picture of the Milky Way? And we claim that our Milky Way galaxy is a spiral galaxy. How do we know that it's a spiral when we have not gone out of the galaxy and taken a picture? So obviously there must have been a process which has undergone in classifying our galaxy as a Milky Way galaxy. And now we call it as a barred Milky Way galaxy. So how do we know that it's a barred Milky Way galaxy? Okay, so to contribute towards the understanding of the Milky Way itself, there are certain projects available at this particular site, which is called as Milky Way at Home project. And Einstein at Home project, it is more about the neutron stars and the interaction between the neutron stars and those kind of things. So depending on one's interest, you can actually go to these sites and then try to learn more about it. And there is always self-help guides available. And even with zero knowledge of astronomy, you can just simply start contributing towards it. Okay, so Zooniverse, it's people-powered research, and the projects are actually pretty simple projects to start with. Even there are a lot of scribing projects also available, wherein the old notes written by the astronomers. Okay, in earlier days, especially in 1900s and in 1800s, people have maintained huge log books where they have simply written the notes, and all these notes are just scanned, and they're all related to various plates, that is the images taken in those days. So we need people to simply translate them into the digital version. So these are called as the scribe projects. Okay, so you can even contribute towards digitizing those past data, which would really help the community. So there are many such projects available under Zooniverse, not limited only to galaxies. It also talks about a lot of planets and stars and transient objects. Many of such data is available. Every time you log in, there will be something new for you to contribute to. So it would be great if any of you could contribute through these projects. This is yet another interesting project which is called as JMARS. It is nothing but it's a Java mission for planning and analysis for remote sensing. What you see here is just a screenshot of the JMARS project, and you can see that here under body, if you select, you have various objects available here within the solar system objects, except the sun. You have all these objects available. There are surface images of these objects available in this particular project. And what you can do is using the tools given in JMARS, you can identify various things. So especially, they're trying to map the craters on Mars. Okay, so using the tools available within the project itself, you can simply map and then try to measure the various craters on the surface of Mars. It's a huge thing, and it is human touch is really required, and that is why we ask the citizens to contribute as much as possible. And once you get into these sites, there are nice helps, and it's easy to follow. It's not really very technical and difficult to do. And if you're really interested in learning more, it is always better to go through this virtual educational observatory. It's a freely downloadable software. It's with preloaded data. Okay, so this data is already analyzed and already well set results are there, but they help you in understanding the concepts better. Okay, so you can just look up as video virtual educational observatory, and it can be downloaded as an exe format. Unfortunately, it's available only for Windows version, and you have many projects in this particular video. And just to give you an example, you can see I'll be showing you a screenshot of a classification of the stellar spectra. Okay, so normally you would have seen the spectra as nice colorful spectra with dark lines and things like that. But here, this is how the spectra of the stars would look like. They look like boring curves with a lot of dips. Sometimes you'll have spikes, which would be like, it is like having emission spectra. But mostly we look at the absorption spectra, as you can see here. And now this absorption spectra, it is, you see various dips. It represents various elements inside the stars. And it's easy to even classify the spectral classification of the stars. And also you can find out what are the chemical compositions of those available in those particular stars. So what you see here in the green region, it is talking about the spectral class of the stars. And on the left-hand side, you see a red cursor. Red cursor is pointing to a wavelength of 3,900, around 3,900 angstrom. And that actually represents to a calcium 2 line, the K line. Okay, so in that way you can understand the composition of the stars, what are the compositions that are present inside the star. So these video exercises would really give you an understanding of how to analyze the stars with already existing data. It gives you a training, okay? And using this training, maybe you can go to the other sites, okay? So apart from that, we have this beautiful app, which is the Aladdin. In Aladdin, you can actually look at various objects in the sky. They are the actually observed objects of the sky, various regions of the sky. You can look at the same object in different wavelengths or as seen by different telescopes. Okay, so one is on the left hand side, it is DSS image, and on the right hand side, it is a Spitzer image of the same object. So it, in a way, you can understand what this particular object is, and looking at its features, there are a lot of things which you can even come to a conclusion with. And there are a lot of tools available online. One of them is TopCat, specially designed for astrophysics, but it can be used in many other ways as well. TopCat, it is mainly used for graphical representation of various things. Suppose if you're studying too many stars together, suppose you're doing cluster study, and if you want to find the proper motion of all the objects within that particular region, you plot a graph. And it is not possible to plot such a complicated thing in our Excel sheet. So it is better to, just get adapted to these kind of available tools for astronomy. One of them is TopCat. There are many other plots. TopCat is available for the Windows system. I'm introducing it because most of us use Windows system, and it is much easier software to use. In other way, what you can do is just the observational astronomy. And observational astronomy is simply by observing the phases of the moon. You don't need extremely clear sky. You can simply look at the phases of the moon, and then you can do a lot of exercises with that. That is one of the parts. And the most interesting part is if you have binoculars or small telescopes, you can start looking at the binary stars. There are plenty of binary stars available in the sky. You can look at the binary stars and then observe them carefully night after night. Are they changing their positions with reference to one star, with reference to the other? And based on that, you can give out some amount of results. One of the famous binary stars, which our ancients also have been observing for very long time, is Mizar and Alcor, which is in the Ursa Major constellation, which is also called as Arundhati and Vashisht, which is very famous binary, okay, and which is used in many mythological stories as well. And it's easily visible to the unaided eye. And if you have telescopes, then you can contribute using your telescope, using getting some beautiful images, and then with those images, you can even do some amount of image analysis work. Of course, this would be at a little higher level. It may be a little involved programs, but to start with, one can actually go through the video programs, and then you can go towards the Zooniverse and those kind of projects. This is just a plot of variability of a star. Variability in the sense, as I mentioned, Polaris is a variable star, which means that its brightness is not constant. Its brightness keeps varying over a period of time. So you can observe how this variation in brightness happens. Even if you don't have the tools for it, there is a site called as AAVSO, which is Variable Star Observatory. The data is posted in this particular site by the amateurs, also by professionals. What you can do is you can simply take the data, plot the graphs, and then try to understand the variability of the stars. The other very easily available tool is the Worldwide Telescope, WWT. this particular software helps us in understanding the sky, and you can even make some nice tours using these kind of sky tours using this particular worldwide telescope software. And you do have softwares like Stellarium, Google Sky Maps. You can use all of them to navigate yourself and get acquainted towards the sky. So I think I've taken too much of time. So with this, I would like to conclude my talk by, I would be really happy if you have grasped something from this particular talk, and if you're ready to jump in to contribute towards some amount of astrophysics.
Thank you.
Yeah.
Thank you, Dr. Sujata Siramulu ma'am, for your nice presentation, and I hope that the young minds, the young students will take away so many information from this talk, and they will definitely may personally contact you through your mail, because you have given your mail here. So
Yes.
who are interested, they can write down her mail also. So there are plenty of questions, but due to lack of time, I don't think we can take so many questions. If you give me permission, let me take one or two questions quickly, or shall we stop here?
Or maybe you can mail me, or maybe in the end of the session. Actually, I may have to leave now, but in the end of the session, if you have some time, I'll join back, and then we can have all questions together probably.
Yes. So, thank you once again for giving us the time from your busy schedule, and hope that in future also we'll have you in physical mood maybe. Thank you once again. Now let me go to our second speaker today. Our second speaker is Dr. Shrema Narendranath ma'am, who is a planetary scientist at the Space Astronomy Group of ISRO. And she's a science PI of the class X-ray spectrometer on the Chandrayaan-2 orbiter. She was a co-I on the C1 Axis experiment on Chandrayaan-1, India's first lunar mission. And she currently leads the Science and Instrumentation Working Group for the ISRO JXA lunar mission in study phase. And she's also passionate about dance, music, and poetry. She is an active member of the International Astronomical Union, and her research areas includes planetary composition, including elemental abundance from the moon, X-ray spectroscopy of solar system objects, solar coronal abundance using X-ray spectroscopy, and astronomical instrumentation. She is also interested in communicating astronomy with the public, astronomy outreach, and astronomy for development. Today, she will deliver her talk on Moon, a very happening place. So we are eagerly waiting to hear you from ma'am. Please start.
Thank you, Dr. Vijay, for your kind introduction. Can you see my screen?
Yes, it's visible. Just one request, please make it a slideshow mode so that this first screen. Yeah.
A very good morning. So I will come very close to the solar neighborhood. In fact, to the closest neighbor that we have in the solar system, Moon. If you think about the moon, it's such a very common object in the night sky, like the first thing that you see in the night. And so we can imagine that from the beginning of humanity, it's been a very common object that people would have been familiar with. In fact, it was in 1609 that Thomas Harriot, who was an English scholar, he used which was then called a Dutch trunk, which was kind of optical telescope, to look at the moon, and he drew what he saw. So if you can see my mouse pointer, so on the left is the original image that he drew, and there is a nice article on this in Nature in 2009. In fact, this looks what he drew is very close to what we can see with the naked eye today. And this is a picture that Galileo Galilei drew very soon of the moon. And in fact, Galileo did a very systematic study of the moon, looking at the different phases, and he could figure out that there are low-lying areas and what he thought was mountains, but highlands on the moon. And many of these depressions that we today, if you look at the moon, even with the naked eye, you can make out that there are these dark areas, which we call the mare, and there are these bright regions, which are called the highlands. So it's the near side of the moon that we see from Earth because it's tidally locked. It has the same rotational period as the time it takes to go around Earth. Because of that, we can see only the near side of the moon. So one common misconception is people talk about often in about dark side of the moon. There is no dark side to the moon. Moon does get illumination except for some areas at the poles. So it's only that from Earth we can see only the near side, but sunlight does fall on the other side of the moon. Mares are in Latin, mare means seas. So when Galileo and the observers of those times looked at the moon with a telescope, they saw these plains which were smoother and called them mare, which really means seas. But today we know it's not that. These are more remnants of volcanic eruptions that have happened on the moon in the early era of its formation. And this Tycho that you see is a very young crater which has these rays that you can see even with the naked eye. So next time you look at the moon with a binoculars or a telescope, do see if you can identify some of these features. A very obvious thing that first time we had a photograph of the far side of the moon from an orbiter was that the near and the far side looks very different. So this remains even an open question even today. One of the reasons we believe is because the crust at the far side seems to be thicker than the side. So these regions which you see as dark are happened because they were very early in the solar system when the planets were all forming. There was an age when there were a lot of impacts. Big asteroids, meteorites, collision was happening in that early era, not only on the moon, but on all planets, including Earth. But then the evidences for that has been erased from all the inner solar system planets. And but on moon, there has not been any a very significant change geologically, or there is no biology there. Therefore, and it doesn't have an atmosphere. So all those things that happened in the past are recorded on the moon. So it's like looking at an old photograph, and you can see what happened about 4 billion years ago in the solar system. So these are very large impact basins that were created by collisions with large meteorites or asteroids, and later on they are filled with molten material from the interior of the moon. So we see that it's compositionally different. The albedo is different. That's albedo in the sense the reflected light that you see between these bright areas and the dark are different, and that's why they appear dark. Let's just look at all the planets in the inner solar system. Moon is very special. So why do we say that? If you look at Earth and Mars, only Earth has a satellite. Mars has Phobos and Deimos going around it, but looking at their trajectory, we know that they are captured asteroids and they did not really form as a satellite around the planet. So only Earth has has a satellite, and it's also 1/3 the size of Earth. So it's actually very difficult to form a satellite as large as the moon. If you do theoretical calculations, you find that it's not easy to form such a large moon for an object like Earth. So that also is a question. right? Like how did the moon around Earth? If you look at the outer solar system planets like Jupiter, it has hundreds of moons. So, for example, Jupiter has all these moons, but their size is almost like 100 the size of Jupiter. So the theory of formation for satellites of these outer planets can be that they just form from the leftover material around Jupiter, just like how the gas and disk around Sun form the planets. What is left over after Jupiter formation form the satellites. But if you look at Earth, we cannot, the calculations show that you can't say that the moon formed from what is left over because of the sheer ratio that you see between, the requirements to make a satellite for an object like Earth. So, what made the moon? What can we do in such a case? You can look at what we observe and then frame a story, or rather a theory of what we think that would have happened 4.56 billion years ago. Because we can't make the story just looking at Earth, because things have changed on Earth. Earth has an atmosphere. It's not the primary atmosphere. So again, we can't say what was it before, like say 4 billion years. In Earth, plants came, biosphere came, so climates change. So we really don't know what exactly how Earth formed or how Earth was at 4.56. But looking at the moon, we can say this. That's one of the prime reasons moon is so important, even to understand the Earth-Moon system. So very broadly, a few points that you might want to consider when you frame a story of how moon formed is moon has a lower density than Earth. Now, how do you calculate density? It's very simple. You learn in school that it's mass by volume. So if you look at how the moon orbits around the Earth, and there's a common point that you can find, you can calculate just by Kepler's laws the mass of the moon. Your radius, of course, you can measure, and if you just do mass by volume, you can get a bulk density. Of course, it's a differentiated planet, just like Earth. It has a crust, it has a mantle, it has, we think, a small core. So the density of each of this is different, but you can make a bulk density. And what you see is that moon has a much lower density than Earth, which means it has lower amount of certain materials, like say iron. Moon rocks have lesser volatile elements. If you look at Earth, the Earth rocks contain a good amount of water. So any rock you take on Earth has water, which is a very volatile element. There are other volatile elements like sodium, potassium. So these are relatively more on Earth. So one of the first thing we noticed from the return samples that came from the Apollo programs is that the moon rocks are very different in how much of water or any other volatile elements that it contains. So explain that for any theory, Earth and Moon have nearly identical isotopic ratios. Now, this is a very important thing in the solar system. At any point in the solar system, the isotopic ratios of certain elements seem to be very fixed. If you like, for example, take oxygen isotopic ratios, we find that for Earth and Moon, it's identical. What that means is that Moon could not have formed at any other place in the solar system, because early on there were theories that maybe Moon just formed in some other part of the solar system, and just like Mars captured these asteroids, when Moon came by, it might have been just pulled by the Earth's gravitational field, and it just became a satellite. But the fact that these identical isotopic ratios exist, that cannot be the scenario. So Moon have to form somewhere in the Earth's neighborhood. There's a high angular momentum in the Earth-Moon system. Which again, all these things are observations that we have. So from this, we have to now make a theory of, or a hypothesis rather, of how the Earth-Moon system would have formed.
टॉयलेट करना है
So what we think today is this. While the Earth was forming very early, about 4.56 billion years ago, a Mars-sized body called Theia, we call it Theia, it had a collision with a very young Earth, and there was what is called a giant impact. And so it's just a pictorial representation. This that was ejected from the Earth, which also consists of material of Theia. All this formed a disk around the young Earth, and which gradually became the Moon. So this is what we believe today, and even today, simulations continue to improve on really can you form such a fractionally large moon. And it's a recent paper where they take a rocky planet like Earth and have a Theia-like body go around it, and they see that very quickly probably we can form a moon-like satellite. Now this becomes also important because as the previous speaker mentioned, there are planets that we see around other stars now in the universe called exoplanets. In fact, every star seems to have at least one planet, if not more. And so there's also this search for exomoons, so which we haven't found yet one. So it also becomes very important in that scenario, like, to understand like what kind of planets will form what kind of satellites around it. It's because the formation of the planet itself seems to be closely tied to the formation of the satellite, especially in the case of Earth and Moon. And all right, we said the story about Theia, and this is how we think Moon formed. Now, how do we find this out? Like, you need to do observations of what are our sources of information to improve upon this or totally change the theory maybe. About the Moon, fortunately, we have a lot more information than about any other body in the solar system. We have 584 confirmed lunar meteorites. So there is a website, the link I've given here, where it's a meteoritic database where meteors, I think there are about more than 50,000 meteorites that's been collected, and all the information about them is available in this website. So in fact, if you really want to look at meteorites and you don't have one in your hand, this is another place where you can go and even just look at the statistics. What kind of meteorites fall on Earth? What sizes do they fall on? What is their composition? How do you find out from which body they came from? So in fact, we didn't know they were lunar meteorites until we had lunar samples from the Apollo missions. So it's after that that we identified that these are lunar meteorites. And now when we get meteorites, we know which one is from the Moon because we have real samples in the lab. So to give an example, some of these lunar meteorites are shown here. Return samples, which have been very important and fundamental in understanding the Moon. The Apollo programs brought back, so there were 6 missions where 12 Apollo astronauts walked on the Moon and brought back material. There is about 382 kilograms of lunar soil and rocks, and even core tubes in which they drill up to 3 meters have been drilled. They bring back the cores with maintaining the vertical stratigraphy. So they're all being brought and preserved. And even today, only 1/3 of that is being really analyzed. Because, that technology is going to improve. You'll have more sophisticated instruments, analysis methods in future. So these have been preserved and kept for future generations. So even 2 years before, there was a call for looking at Apollo samples because a new box was opened. And so there is a program called ANSWER where scientists from around the world can write proposals to get Apollo samples. So if you really have a very good scientific investigation planned, you have instruments, you have resources to do it, you can ask for these Apollo samples. They are invaluable, of course, so that responsibility is also there. And we had we had, while Apollo astronauts brought back some samples, there were also these robotic missions by the Russians, which were the Luna programs, which brought back 320 gram of samples without humans. So they had robotic missions which brought back these return samples. And we have some of this at the Physical Research Laboratory in Ahmedabad. We have shared from this program. Chang'e 5 is the latest in the return sample missions after almost 50 years after Apollo, which brought back 1.75 kilogram of material from a very interesting region on the moon. I'll come to that later on. So each of this sample, have been, every grain has been studied, sorted, all kinds of mechanical properties, composition. All of this have been studied, documented. There are thousands of papers on this. The data is archived. These all are fundamental things that we have to understand the science of the moon. And a very important thing that the world is looking at is if we can have a sustainable working environment on the moon in future. Because this is the nearest accessible place for humanity, and hence, the whole world is towards having permanent settlements on the moon. So even in that context, this is an important resource that we have. Next best thing to do, because return samples are, if you want to send people there and bring back samples, that is obviously a very expensive program, and that's why it doesn't happen very often. The next best thing you can do is to do in situ measurements, which means send a lander, a rover, and put instruments on that, and they measure and send us data. So that's been also done. Again, all these measurements are archived and accessible to everybody in the world. Remote sensing from an orbit is equally important because, however many instruments that you send in a rover lander, you are again restricted to perhaps a few kilometers around that landing area. You're still, moon is very big and you're still sampling very local compositions, but very precisely. So you can never cover the globe like this, even if you send hundreds of missions. So you do need remote sensing measurements for that larger view, and then connect it to what you find very locally and understand how diverse is the moon actually. Currently there is a reconnaissance orbiter that's been around the moon by NASA. We have our own Chandrayaan-2 orbiter, and recently there is a Korean orbiter that's just started taking scientific data around the moon. And of course, ground telescopes are still used to study the moon. For example, the water signature on the moon is being studied by an aircraft-based observatory called SOFIA. Some of the ground telescopes, in fact, we also use the Kavalur observatory to look at the very thin exosphere of the moon. Exosphere is that region just above the surface of the moon where the densities are so low that atoms do not collide at all. So it's called an exosphere. We look at, we do observations of the exosphere of the moon from ground. Now, some early revelations about the moon was that moon is an evolved differentiated body, which means it has a crust, mantle, and core. So that's a major difference between asteroids and and a planetary body, because asteroids are homogenic in the sense they're not differentiated. So to differentiate, they need to be liquid at some time in its past. They should have been a liquid, and that's why when denser materials can sink and lighter materials can float, and this fractionation happens. So we know moon formed very hot. Moon rocks are older than Earth's, so that shows that they have not changed very much. So if you date them precisely from these samples that are brought back, we know that moon rocks are older. Moon formed in an anhydrous environment. So if you look at the composition of the moon, we know that it the rocks or the minerals that formed don't need water to form. It's very different from the case of Mars. Some of the evidences on Mars show that some of these minerals have to form in the presence of water. Moon's surface is covered by a thick regolith, which shows that it's been battered by impacts past, and Moon does not have life. So this is what we believe that happened early. The young Moon was molten, and there must have been a very small metallic core, and then in liquid magma, heavier elements sink to the center and form such olivine and pyroxene, which are minerals that contain iron and magnesium. So these are heavier and they sink to the bottom, which means now you form crust, mantle, so you form those separations, and lighter materials that floated to the surface became the crust. And the samples that we bring back also shows us very unique things that belongs to the Moon, like, for example, what you call agglutinates. So these are these black, kind irregular shaped pieces in the soil. So this is a sample of the Moon regolith. So regolith is just a debris, which is unsorted, which have grains of range in sizes. So when you say soil in really technical terms, you're talking about very fine micron size particles, whereas regolith is a mixture of all this. So they have these agglutinates which form because of solar wind and micrometeorites, keep on falling on the surface of the Moon, and very locally it increases temperature, melts the soil, and again fuses it. So agglutinates form like that. There are these green glasses which were brought back from Apollo, which shows some volcanism was there on the Moon, and they form because they cool very fast. So this is just a close-up of a glass sphere. And today, these lunar soil, this is just one grain of the soil being studied using X-ray tomography and CT scans, which shows, without damaging the grain, the inner structure. So all this tells us a story. And this is one of those cores where you can, so that's the surface. And as you go down, you see, sometimes compositions change, sometimes densities change. So all of these are used for this. Now, I'll just concentrate on some things, what we understand from the Chandrayaan missions. One of the major discoveries that we have from Chandrayaan 1 is that there was water on the Moon. So very early, as I said, the revelation was that Moon formed in a very anhydrous environment, and there is absolutely no water on the Moon, except for the poles, which has very unique places called permanently shadowed regions. So except there, we never had an idea to look for water anywhere else on the Moon. But then the first such widespread possibility of water molecule on the Moon came from, as a surprise, from Chandrayaan 1. It's a moon mineralogy mapper flown by NASA and university. So it came to them as a surprise. They found a particular line, absorption line of water. So if you are MSc students, you would have studied about vibrational spectroscopy, where the water molecule, which has a shape like this, it has these bonds. So this line comes from OH bond vibration. How do you get this? The sun's light illuminates the surface of the Moon, and you look at it from the satellite. Some of this is absorbed by the vibrational bond at a particular wavelength. So a band at 3 micron in the near infrared is indicative of the presence of OH. So that was mapped for the first time, and that was a big surprise that Moon seems to have water, not just at the poles, but everywhere. Now, again, this doesn't mean lakes or oceans, just talking about water molecules at ppm level. ppm means parts per million. So if there are 1 million molecules, in that maybe 100 molecules of water. But again, still, this was a very important discovery because there was no such thinking in the past. So where does this water come from? And then it was also observed by the same instrument, by others subsequently, that there seems to be changing as well. So the abundance of water, or how much water is there in the morning or midday of the moon, seems to be changing. And it's different at different places. So again, if you want to understand how the moon is formed, then you should also be able to explain these changes that's happening with seasons and day and night on the moon. There was this question that, okay, you have this OH bond, but does OH bond really mean H2O, or be an OH bond and something else? So the Chandrayaan-2 carried a spectrometer where we extended this band up to 5 micron, and then it mapped very well. And today we know, really, yes, this is indeed that 3 micron feature from water on the moon. So Chandrayaan-2 is continuing to map the moon, and this is some of the latest results, where this is a crater in the south pole of the moon called Shackleton. It's a permanently shadowed region, which means these are the coldest regions in the solar system. So, actually moon has the coldest place in the solar system, and inside these PSRs, it has not seen sunlight for more than 4.5 billion years ago. Because of this, this is a very enigmatic region, because you're not able to take a picture inside. There's no illumination, but we believe, just by looking at the temperatures and certain measurements that's been done over the last decades, that it should contain water ice. But what we have here is just the rim of this crater, and you see indication of water abundances. Very recently, it was in the newspaper that the Chang'e 5 glass beads, they seem to have water, and they propose that this water in the glass beads form because solar wind interacts with the surface of the moon, and so these water molecules then diffuse inside these glass beads, and then they get buried in the soil. So they propose, if you actually had this happening for billions of years, you must be having a lot of water on the moon. They estimated 2.7 into 10 raised to 14 kilogram of water, which is quite a lot for the moon. We also found water in the exosphere of the moon. Again, I'm concentrating on surprises here, because these are the things that changed our outlook on the moon, and moon became a very hot destination today and for the future. There was a mass spectrometer on a moon impact probe on Chandrayaan-1. It was just, it had only a short observation. They found water. This is 18 AMU, which means water. It suggested that even the exosphere, which is the thin atmosphere of the moon, seems to have water molecules. Water rise at the poles using radar was done in Chandrayaan-1. So again, this is a view from the top, showing the north and the south pole, and some of these green marked craters were seen as anomalous or possibly containing water ice. So the quest for water, and how much of water, we know for sure there is water ice at the poles, and there is indeed water molecules everywhere on the moon. But what we don't know is how much is this quantity and where is it coming from. Again, some of this water seems to be from the interior of the moon, as was shown in this paper, again using the data from the M3 on Chandrayaan-2. Just by looking at the context or where you find it, they argue that this must be water from the interior of the moon. So volatiles is not just about water. Sodium, for example, is a volatile element, or at least moderately volatile, and so it's less on the moon when compared to Earth. So Chandrayaan-2, but mapped for the first time the distribution of sodium, and what we find is probably there is a volatile component in this, because you find higher sodium at the poles, and also find some changes with seasons, just like water, with which we propose that probably.
Hello.
Yes.
Now, what is this CH2 class?
Okay. So CH2 is Chandrayaan 2. Sorry.
Thank you.
Yeah. Yeah. So again, as I said, because we didn't find in any Apollo samples any minerals that required the formation of required formation scenarios required water, we had this idea that Moon did not have much water. But then this is another surprise that you have from the Chandrayaan-1 data, where you find hematite, which is like oxide of iron, which needs water to form. It's like rust. And these red areas that you see here are hematite, and you see at these poles, local, they have detected locally some of these hematites, which again shows that perhaps our ideas in the beginning were probably not completely correct. Now, composition of the moon is another thing, both for understanding its formation and even for our future, planning things on the moon. You need to know what is the soil made of. You need to know material strength. For any activity on the moon, this is an important thing, apart from the huge importance in terms of science. But the composition is very diverse. So it's not just mare highlands, as we thought very early on. The composition is quite diverse. The color here, for example, just indicates the presence of these magmatic materials. So here you see this part of the moon is quite different from the rest. And this diversity is at all scales. So if you go with a rover and look at every grain, that's going to be different. These are meter scale. You see, again, this is from Chandrayaan-1 data. There's a crater here, to give an example, and around the crater there is an ejecta. If you see a visible image, you just notice these bright regions. You translate that to mineralogy, or like what minerals are around it. You see that there is an asymmetry here. There's kind of a melt here, etc. So a picture like this with compositional mapping tells you about how this would have formed, what thermal processes it would have undergone through. So mapping minerals and composition thus becomes very important. Again, from Chandrayaan-2, a magnesium map of the moon, which is really a first time map. And you see it's continuing, so it's not filled up here. These shows these tracks with the color indicating the amount of magnesium. So you have these high magnesium areas in some of these mares. The size pictures again tell you a lot. This is a buried lava tube that you see here. There is a stretch here which is buried. This is a relay, which means here there has been some flow of impact melt. And with Chandrayaan, we were able to create 3D maps from stereographic views. This is from Chandrayaan-1, and in Chandrayaan-2, we continue to do that and is providing globally such 3D maps. You can see the very deep crater here, and you get these heights, which is what gives you that 3D feel for it. This is a image of a South Pole region from a radar. Radar is very important because it just, while an IR spectrometer or a visible spectrometer tells you about the surface, IR penetrates deeper. So we can see craters that are buried or below the surface. These are, the radar scattering also tells you whether these craters are fresh. It also helps you look for water ice. So this is again from CH2 or Chandrayaan-2. Moon is very special in this, as I said in the beginning, but one of the reasons is also because Moon has a lot of craters, and this shows us the 4.5 billion years of history. So just to if you look at Earth, this is a crater that you all must be familiar with. It's the Lunar crater. This is Venus, and that's Mars. You can see how much they have changed in the past billions of years, whereas on Moon, once there is an impression, it's well preserved. And since we have real dating of samples from the moon, we can connect them. The moon forms the basis for the whole chronological record in solar system. So it's on the basis of moon that we date everything else. Until in future we'll have Mars samples. And this is from Chandrayaan 2 terrain mapping camera. Again, a very beautiful 3D image where you can see the depth perception, you can see the illumination, you can see these very small craters. They are age indicators. So why craters are so important is because there is a method called crater counting by which we can say a surface is new or old. So these two are to show that. This is another image from the Lunar Reconnaissance Orbiter narrow angle camera where you can see these do not have many craters. It looks very fresh. So counting the craters is one way of saying whether a surface is old or new. Because older the surface, more the number of craters, and younger would be it will be very fresh. This is just a close-up view with orbital high resolution camera on Chandrayaan 2. This is the highest spatial resolution camera that we have around the moon. So it's each pixel you can get 25 centimeters. So this view you can see these very small rubble and boulders that's around this crater. These kind of images are important for science, and also like tomorrow you want to choose a landing site. We need to find a landing site and a rover path planning. All these images become very important. Recently, it was also found from this Chang'e 5 basalts that return samples that the volcanism on the moon lasted for a long time, and the Chang'e 5 basalts, because we brought them back, we could date them very precisely. They are only about 2 giga years old, which means volcanism lasted for a long time. So the question is, the moon which was cooling, where did it get all that heat from? There are many evidences, even by remote sensing data of young lunar volcanism. I'll just touch upon the other part, which is the exosphere of the moon, where this is again from Chandrayaan 2. We found very interesting results on the exosphere part of the moon. There seems to be a dust layer. They mapped the total electron density in the exospheres. Again, these used just communication signals from Chandrayaan 2. The Chandrayaan 1 found some mini magnetospheres on the moon. Moon doesn't have a global magnetic field, but then there are localized regions where solar wind is reflected more than in other regions, from which they found there are these small localized regions. The exosphere of the moon, as I said, was briefly looked at from Chandrayaan 1, and they measured these different gases in the exosphere. This is hydrogen, that's neon on the left, and with Chandrayaan 2, it's still happening. This is the first global map of argon on the moon. Argon is a noble gas, and so this again indicates some activity on the moon, because we believe these are outgassings from the interior of the moon. This is again from Chandrayaan 2. So you see that this is Earth and this is moon. And if you look at these lines, which are magnetic field lines of Earth, and the solar wind comes from the left side, what we find is that every time moon passes through this part, which is called the geotail, which is really going through the magnetic field lines of Earth, you see these bursts of electrons, which is a very new observation, and this is in preparation. So I'll come to the end of it. We have a future at the moon. So the takeaway is that our initial understanding of the moon as a very, quiet and nothing much happening place, with many of the observations in the last decade, there is still a lot of things that we don't know about the moon, and it's very important to know because we have a future at the moon. Already talk about properties on the moon. There is research going on how to do photosynthesis at the moon, because if you really need to have a sustainable environment, this is all important. For example, Chang'e 4 took cotton plant seeds in a very controlled environment, and it did sprout. That's a photograph of that. And this is a recent paper where they were growing thalicrus, which is a common weed, which has a very good genetic sequence, which is very well known, and they grew it in these Apollo soils, and JSC1A, which is a simulant, to see how it affects its growth. So it looks like Apollo 11 soils or 12 was better than 17. These kind of thinking has really become reality. So that's the last slide. From what Buzz Aldrin, the second person who stepped on the moon, said, beautiful, magnificent desolation. Our future at the moon seems to be very crowded because the world is now with the Artemis programs, India's own lunar programs, Chang'e programs. Japan is having another satellite to moon very soon this year. So we have really a lot of activity happening at the moon, and it is towards actually building permanent settlements on the moon. Yeah. Thank you.
Thank you, ma'am, for such a beautiful talk on such a beautiful topic, and the people's curiosity to know the beyond Earth. And I can remember the word of Neil Armstrong when it said that on July 20, 1969, he landed on the moon, and like that's one small step for man, one giant leap for mankind. And from them how these revolutions comes through this ISRO and NASA, and you all are doing such a tremendous job to give us like in more information on this topic. We'll hope that in future also we will get some more interesting thing, and one like may go to someday the common people like us may go to visit moon also one day.
Yeah, I'm sure it will happen. Yeah.
Yeah, that might be happen in near future also. Who knows? So I request at this point Dr. Shorkar to ask from the participants any question or any queries, or they may directly interact with the speaker.
Thank you, Dr. Vijay. Dr. Sharma, there are some questions in the chat box. So Sanjukta is asking, ma'am, what would happen if there was no moon? How does the moon affect Earth?
That's a very good question, and that's something also make us want to understand the moon. So if you look at moon, first thing, the moon is really receding away from us at about 3 centimeter per year. So if you calculate back, moon was very close to Earth. So the rotation of Earth and moon are very much tied. So long back, Earth and moon were rotating faster. Our day and night cycle is really tied with the moon, because you have an Earth-Moon system with an angular momentum shared, and how exactly moon orbits Earth matters to us, and about the tides. So there is even this thinking that actually sea animals really came to become land animals because of these tides. That's one reason. In fact, even there are many interesting things, many reproductive cycles of even humans, as well as fish, and many species seems to be tied with this 28-day cycle of the moon. Just to give a few examples, but certainly, the formation of Earth and moon is very closely tied. And so moon is something that today we believe may be actually needed for habitability on Earth.
Thank you.
Hello, madam. Hello.
Hello, please tell me.
Am I audible?
Yes.
Actually, I want to know, means this NASA's landing on the moon by Neil Armstrong, it is how much true? Because in the moon, the situation is quite different, and it is still debatable.
No, so to give a short answer, there is no question of whether that's fake. Even though there are a lot of websites that might claim to do that, you have these samples in hand. So you just need to look at those samples to understand that you cannot make any of these things in the lab, in any terrestrial lab. These materials are made in no magnetic field conditions, no water conditions. If you make some material, you cannot do it in that circumstances. And these, as I said, are available for scientists internationally. So, we cannot really make such a fake thing for the whole world. These are open to people. Just that samples tells you that these are really true. And it's not just
and
only
in
one
future
mission.
people,
Sorry?
hello,
Yeah.
and in future people are planning to stay in moon. So how much it will be successful according to you?
Certainly, this is inevitable and it will happen in the maybe next 50 years. I mean, just giving a number, but the Artemis crew is ready to go. They just announced the name of 4 people who's going to the moon. So this is a global effort, and we won't talk about whether India goes or Japan goes. This is a whole humanity going there, and since it's revived now, that because today we know that if you want to go to even Mars, better really have some permanent place at moon, because that makes it a lot easier. And this is the nearest body where you can test out all your technologies, really do things. Is closest thing is moon. So definitely I think this would become unavoidable, and in the next 30-40 years I'm sure this will happen.
Dr. Shyama, there is another question from Ansal. Do you believe that moon once had an atmosphere, madam?
Yeah. So even for Earth, we don't really have our primordial atmosphere, because initially it was so hot in the solar system at that time that all these have evaporated away. What we have is a secondary atmosphere that's come from outgassing. So there is a debate on it, because moon did have volcanism for a long time. So it is quite possible that it did have a transient atmosphere at some point from these volcanic gases that came out of the interior of the moon. So it's more theoretical now, but many evidences show that it should be having one.
There is another question from Sanjeev. Earlier, a day would last 21 hours instead of 24 hours. Is it true?
Yes. So that's what I said. Because as moon is moving away, the rotation rate also changes. As you know, closer it is, Earth will be spinning faster. So we'll be having shorter day and night.
We have 5 more minutes. Can we take some more questions if you...
Yeah, I'm fine. And maybe I'll stay back and also look at the chat for some more time.
So then Vishal is asking, can we use nuclear winter idea to make moon habitable for the future?
Nuclear?
Can we use nuclear winter idea to make moon habitable for future? Nuclear winter.
Nuclear winter?
Yeah, so this term is new for me also. Maybe Vishal, if you can unmute yourself and ask your question.
Vishal, can you tell me about nuclear winter? I'm not sure what winter means.
Are you there, Vishal? Vishal Bhattacharya? Okay, maybe we can take up the next question by Anukalpa Bhaumik. So I wanted to ask, is it possible to bring samples from the dark craters of moon that receive no illumination or sunlight?
Yes, that's something that we all want to do very much. But as I said, it's incredibly cold there. There are concepts, but when you say cold, you're talking about 20 Kelvin kind of temperatures. So the moment you touch it itself, it sublimates. But certainly this is something that we want to do. Currently, the technology doesn't allow you to do it, but in future, probably yes.
There is another question from Rakesh. Hello, ma'am. How is the research in ISRO going on related to these theoretical aspects of astrophysics and astronomy? as the public majorly knows about the commercial achievements of ISRO regarding satellite launches and some other.
So yeah, we do have research happening in not more than theoretical. It is more practical applications. So we do build instruments into many of these topics, and we have laboratories. We look at data from these ongoing space science missions. So there is a very diverse in astronomy, planetary science, atmospheric physics. This is indeed happening. More majority is on practical applications and instrumentation rather than the theoretical part.
So the next question is from Arup. So has the moon any ionosphere?
So it was not thought in that terms earlier, but like the paper that I mentioned, Tripathi et al., which is a group from SPL in the SSC, which is a part of ISRO, they have shown with some recent measurements that moon seems to have a very, even though thin, an atmosphere. You should read the paper.
So there is another interesting question. There are controversy of rich people buying lands on the moon. Is that true?
Yeah, I don't think like today you can sell really, because moon belongs to humanity. We really don't think that's happening now. Yeah, I also see such websites, but really I don't think it's really happening.
Bharti has also asked another very interesting question. Ma'am, is there any possibilities of microorganisms to sustain in moon? Do any research been done on that?
Yeah, so I think in in the sense, basically they need some source of energy. So in a controlled environment, possibly yes, but we don't have any evidence for any microbial population in any of the return samples or any in situ measurements. But then the other possibilities, because we never have gone into a PSR, the permanently shadowed regions where there could be water ice, I won't bet on it. But as far as we know, there is no microbial life on the moon.
Hello, madam.
Yes.
Hello.
Yes, please.
Madam, I want to know the concept, how the Chandrayaan 2 was landed successfully on the moon, which how the gravity has been maintained appropriately for landing.
So if you want to land something on the moon, they need to do precise calculations of the trajectory, when to release it from the orbiter spacecraft, which means you need to know the gravity field of the moon very precisely. So that has been mapped by a spacecraft called GRAIL. We do have models from GRAIL, which tells you how the gravity field of the moon changes, very high spatial resolution. From that, flight dynamics experts calculate the trajectory very precisely, and then you keep sensors to have guidance automatically. I mean, you look at how the trajectory is live and correct for any small perturbations. So it's a very complex process. I mean, in a nutshell, this is how you would do it.
What is the software you told?
Oh, okay. I mean, it's not like a specific, it's not like an open source that I can just tell you, like. Okay. So this is a more complex indigenous things that are done.
Shall we go for one or two more questions, because there are plenty of them? Maybe you can yourself see in the chat box and try to answer.
I'll see that. Where did we? Okay. How is the ions formed? There is from Devjyoti. How are ions formed on the moon surface due to radiation? So just like if it causes ionization, ions will form, right? So it's basically just that. Any high energy radiation which can break the bonds and form ions, it will. The sun has UV radiation. Since there is no atmosphere to stop any of this, or in Earth's case, it does. This can happen. What are the criteria? Abhinav was, what are the criteria of the surface that the space agency makes sure while landing lunar or a Martian mission? Yeah, so again, primarily there is engineering constraints, like you want illumination to be there on the landing site while it lands. If particularly if you are looking at solar power to power it, you need the surface to be, the slopes you don't want to land on a very inclined surface and topple over. So you want to first look at the slope, and like for that particular rover that you have designed or the lander you have designed, you will have a number like I want the slope to be less than 15 degrees or so that criteria. And you want there is something called an error ellipse, because again pinpoint landing is one thing. So if you want to maintain an error in your landing, you want that much area to be clear of boulders, have this kind of slope. So you should know the topography, etc., etc. And also then the scientific importance. After doing all this effort, you want to make some measurement that is a breakthrough. So it's a combination of all these. The barrier, as the great barrier, the
Just
great
one
impact.
announcement, like we wish to take one picture
Oh
uh,
yes.
along with the speaker. So those who would like to come into the picture, so please unmute your camera so that we can take one picture. After that, we'll
Yes,
go ahead.
that would
Yeah,
be
I think
great.
we should stop. It's 11:33. I'll just reply in the chat to the rest of the questions.
Ma'am, in the meantime, you may answer one last question so that they may prepare themselves for the picture.
Great impact theory says moon comes from the collision of Earth. Then why didn't the moon have any living organisms, but Earth has millions? So even Earth's life, we really dress again. There are so many whys, but so even on Earth, we don't know really how life started. Right? So at the time of collision, at those times, definitely Earth's life started much later. So on moon. At that time, certainly there is no possibility of any living organisms. Even on Earth, it's much later when by exactly times, but yeah, it's much later that we had life. And how did the first life come is again a question. Yeah.
Okay, so
Yeah.
yeah, maybe the other participants also can turn on their video. So let us take a group photograph. We're requesting the participants to turn on their videos. Okay. Yeah, so we'll take
So 1, 2, 3.
So the next one, okay. Yeah, so one more. Thank you very much.
Thank you. Thank you to the organizers. It was a very nice session. Thank
Dr.
you.
Shyama, thank you very much for sparing your valuable time and delivering
Thank you.
such an interesting talk. So see you again sometime in person.
Thank you.
So as a chairperson of this session 1, I conclude this session here. So thank you all for your precious presence and to carry forward these nice talks. Thank you all. We will meet you all in the second session.
Yeah,
Chaired
so
by
second
Dr.
session will start at 2:30 sharp. So we look forward to your presence in the next session after lunch session. Thank you.
Thank you.
Hello.
Yes.
Sir, is it possible to share these slides?
Okay. I will request the speakers. So if they agree, then maybe I will request. Maybe tomorrow or day after tomorrow. Maybe after the sessions are over, I will send them a request. And if they agree, then I can share with you all. Is that okay?
Okay, sir.
वो वाला दे दो अभी इसके लिए तो स्क्रीन शेयर कर दो पोस्टर का स्लाइड शेयर
थोड़ा लैग हो रहा है।
स्टॉप प्रेजेंटिंग करो तो स्टॉप प्रेजेंटिंग मैं प्रेजेंट वो कहाँ है इमेज इमेज कहाँ है ये वाला उनके एंटायर स्क्रीन कर रहे थे नहीं करना है ना एंटायर स्क्रीन है विंडो करना है स्क्रीन शेयर मत करना विंडो करना ठीक है उससे भी एक प्रॉब्लम हो रहा है
इसे पीडीएफ है तो पीडीएफ दिखा दो
मैं करता हूँ तुम मत करो ठीक है मैं करता हूँ
Thanks.
हो गया ऐसे ठीक है क्या हुआ उससे विंडो करो ना एंटर स्क्रीन मत करो शेयर विंडो कर दो
Next.
ठीक है आ गई लैपटॉप कितना खराब हो गया एक बार कर दो
खोलो मत, खोलो मत, वो पूरा वो रोशनी आता है।
We've done, she's explaining. For the intent हो गया भाई और कुछ कर दे one thing that you are to join, say participants, please start joining. Okay.
স্ক্রিন শেয়ারিং স্টপ করে দাও।
Hello, Sonali.
Hi.
Hi.
So, shall I try to share?
Yeah, sure. Stop. Yeah, let us stop sharing this one. Yeah, now you can share.
Your entire screen, a window, a tab. Your entire screen.
You may share a window. You may share the window only.
Oh, okay. A window. Oh, okay, got it. Share. Okay, then how do you go full screen? View. Full screen. Oh, but I can't see you. Wait.
That's okay.
But view.
It was coming full screen when you did that.
Slideshow.
Okay.
Okay, this is full screen, but I can't see anybody.
I think it goes like that only.
Oh, I see. Okay.
But we can clear. Your slides are changing and everything is fine, working fine.
So you are changing my slides?
No. I mean, you are changing yours.
No, I am not changing. Oh, okay. Because I went for slideshow, it is changing itself. Okay. Then I should go for that full screen mode only.
Yeah.
Okay. Now it will not change on its own at least. Okay. Yeah. Okay.
So how is the weather in Bangalore?
Bangalore is always pleasant. It was
Right.
hot for some time.
Yeah.
But then now it's going to be, it's raining. I mean.
Okay. We are also having rain here since some days in Tezpur.
Okay. I visited Tezpur University quite a lot of times.
Okay. Yeah.
Because, do you know Roop Jyoti Gogoi?
Yes, I do know her.
So she is a very good friend of mine.
I guess you have some papers together.
And she used to visit, in fact, she visits IUCO often because she's an associate there.
Yeah.
So I met her there.
Great. Maybe, yeah. I'm also an associate of IUCA.
So you'll be visiting there soon?
Yeah, in July.
And also they organize a lot of workshops.
Right. Physics department organizes a number of workshops.
Along with IUCA.
We'll wait for a couple of more minutes
Yes,
and
yes,
then we can start.
yes. I think it's just 24. It was supposed to start
Right,
at 2:30, right?
right. Participants are still joining in on Google Meet. So Sonali, shall we start?
Yes. Shall I
Okay, no,
share?
no. Let me give an introduction of you, then we'll start.
Okay.
So, welcome back, dear participants, to the second session of the workshop. So, now we have Dr. Sonali Sachdev, who is a postdoctoral fellow in astronomy and astrophysics at Raman Research Institute, Bangalore. She is an active member of the International Astronomical Union. The broad area of her research relates to the formation and evolution of galaxies. Her expertise lies in the determination of the structural parameters of galaxies in optical and infrared wavelengths. Using these parameters, she studies the correlation of the different structural subtypes of galaxies with their star formation activity, environment, and other properties. This has enabled her to produce significant results regarding their evolutionary pathways. Other than research, Dr. Sonali is interested in astronomy education, the sociology of astronomy, and communication of astronomy with the public. Today, she will deliver a talk on science of galaxy formation using JWST. So I welcome Dr. Sonali Sachdev to deliver her talk.
Thank you for the nice, kind introduction. So you can see my screen, right?
Right, yes.
But it's not full screen.
No.
So now it is full screen.
Yes, yes.
Okay, okay. So so first I would like to begin by thanking the organizers, especially Biplab Sarkar and the Tezpur University for providing this platform. It's really a privilege to present our work to such an audience. So what I'll try to do here is give a very basic, very introduction to how we try to know about the galaxies in the universe, and how the telescopes that we put help us in achieving that. So in each telescope there's decades of hard work, there are billions of dollars that are spent. So how those telescopes help us in this endeavor of trying to understand how the universe began, how the galaxies were formed earlier, and how they have grown to the present stage in which we see them right now. So let me begin by showing you this. These are some of the by local I mean like they are present right now. They are in this form. So the galaxies that we see right now can easily be put into one of the categories, one of the classifications based on their structure. So this is called the Hubble tuning fork diagram, and once you see a galaxy, you can see that there are spiral arms, or you can see that there's a bar. So based on those kind of features, or whether it's an featureless elliptical, you can place them in one of these categories. So these are with bars. Here the spiral arms become more and more prominent. Here the bulge becomes more and more prominent. Here there are no spiral arms. It's more of a it's a blob. It's more of a spheroid, like a football. How the stars are placed here determines the shape. Means if it's a spheroidal, if it's an elliptical, then the stars are countering gravity through random motion through velocity dispersion. But here the stars are in rotational motion, they are confined to a disk, so that forms a spiral, like our Milky Way is a spiral. So so the galaxies that we see now, that have, so now the age of the universe is 14.7 13.7, so let's call it 14 billion years. So this is how galaxies look when they are 14 billion years old. But we can also see galaxies when they were younger, when the universe was 6 to 7 giga years old, means half the age it is now. So how we are able to see it is that these galaxies are far away, so when they emitted the light, the galaxies were much younger. So as far away we see the more younger universe we see. So that that light takes its own time to travel to reach us, has enabled us to see galaxies at younger ages. So this is when the universe was half the age it is now, and we talk in terms of redshift. The redshift now is 0, and redshift at that time was nearer to 1. So we can see that the shapes are not as well defined as we see them now. So as we go to higher and higher redshift, we actually see younger and younger stages of galaxies. We can actually see them growing in size, growing in mass. So that gives us an understanding that we can trace the evolution of galaxies. We can trace their formation, we can trace their growth. So for example, now let me go to a little more higher redshift. More higher redshift means the universe was just 2 to 3 giga years old when these galaxies, these galaxies are from that age. So you can see that you cannot put them in any defined structure form. The Hubble tuning fork diagram where you place galaxies, you can't place these kind of galaxies, but when you do their structural analysis, you can see that, oh, they have a disk, they have a bulge. For example, in this kind of the galaxies that we see now, these kind of galaxies, there is this Galaxy Zoo program where all the citizens can also classify galaxies just based on their broad structures, because it is easy to do. But as we move to higher redshift, they become less defined, they become like a blobs, and so it becomes impossible for anybody to determine what kind of structure there is unless you do a very refined analysis of the same. So what these snapshots in different years reveal is that we are seeing the population at different ages. So here universe was 2 billion years old, we see small blobs. Then 5 billion years, we see slightly more refined structures. Then 9 billion, we see more refined. And then 14, which is now, we see fully formed, proper, regular ellipticals and spiral structures. So this is like if suppose you are an alien and you are sent to Earth, so you can see human population, you can see kids, you can see people who are adolescents, then adults, then so what you have to tell is which kid will grow into which old age person. So which galaxies will grow up to be ellipticals, which galaxies will grow up to be spirals, and what are the mechanisms that are going to lead into that, means which physical processes is it going to be mergers, is it going to be accretion of matter from outside, is it going to be some internal adjustment of matter. So which are the processes that are regulating this growth, and so this is what we try to study, and this can only be done if you have telescopes that are able to see further and further. For example, even these galaxies that you are seeing, we have been able to see in the optical only in the last decade, because let me show you this one. Oh, wait. So in the last decade, so earlier there were these ground-based observatories. Then Hubble Space Telescope came. Then it it focused on a patch in the sky, and so we saw a lot of galaxies there. And then in 2010, it got a new camera, Wide Field Camera 3. So it had some infrared filters, so we were able to see in the infrared. So hence we were able to see high redshift galaxies in the optical. So what happens is that when a galaxy is far away, its light gets redshifted into, means its light the light that was supposed to come to you in the optical reaches in the infrared, because it gets expanded. So we need infrared telescopes if we need to see galaxies in the optical. So that has also happened in the last decade, that we have been able to see those galaxies in the optical. So this kind of understanding has also developed over the last few years, because earlier our understanding was that all the galaxies can be placed into nice categories, but then we discovered that most of them are irregulars, and we can actually trace their growth history. So there are two things that are important when you are studying galaxies that are far away. So one thing is that one thing is that we have to take care of the different distances in cosmology. So suppose there is a star of luminosity L. So there's a luminosity distance, means how much light the star has traveled to reach us, and then it gets divided into the area in which it fell. So the flux that we receive is L upon 4 pi r square. Then there's another distance, that is the angular diameter distance, means what angle is did the object form when it emitted the light. So these two distances would have been same if the universe was not expanding. But because we live in a cosmologically expanding universe, these two distances are not same, and we go through cosmological surface brightness dimming. So what I'm trying, I will explain it very slowly and very in detail. So you see, flux is luminosity upon 4 pi, the distance square. So this is luminosity distance square. And the solid angle that is subtended by the source is tau, which is A by angular diameter distance square. Now, if these two distances were same, then surface brightness should have remained same. Surface brightness from an object, if a bulb is near you or if a bulb is far away from you, surface brightness does not change. It is the intrinsic parameter. So, but because these two distances are not same, because we live in a cosmologically expanding universe, what happens is when you do flux up, we try to find the intensity, the surface brightness, we get a 1 plus z to the power 4 factor. Z is the redshift. So when the universe was half the age it is now, redshift was 1. So suppose I take a galaxy, which is right now here, and put it at a redshift 1 when the universe was half the age it is now, then its intensity, its surface brightness falls by 1/16th, and that happens only because there is a cosmological expansion. So because of that, we have to also recover that. Anyway, the galaxies that are far away must have been less massive, were less. So they were anyway going. It was anyway going to be difficult to detect them. But because of surface brightness dimming, it also increases our task that we have to create telescopes that are able to go fainter and fainter. So that is what I was telling you, that we create telescopes with larger and larger aperture. Larger aperture will be able to grasp more photons in a given exposure time. So that's why the future is here. This James Webb Space Telescope. So from 2.5 meter, you have gone to 6.5 meters. So you have to go to you have to create telescopes with more and with larger and larger apertures to catch more and more photons, so that you are able to penetrate deeper and deeper into the universe. You are able to see earlier galaxies which are dimmer because of cosmological expansion. But one thing that helps us is that this angular diameter, it does not change with redshift. It does not change if the object moves far. Means if suppose there's a galaxy that takes 5 arc seconds, if it's a 5 kiloparsec galaxy and it takes 5 arc seconds at redshift 1, even at redshift 10 it will take 5 arc seconds. But let's not get into that. It's just one of the things that actually helps you because the universe is expanding. But this one thing, that the surface brightness dimming takes place, that you need deeper and deeper telescopes, you need better and better telescopes. And another thing that happens when you have larger telescopes is that your resolution improves. You see, this is the same image taken by Weiss. Weiss was this earlier infrared camera, then Spitzer came, which had a better angular resolution. Angular resolution means this angle to which you can resolve. So that became even better with JWST because it has a larger aperture. So so, and then as I told you, it is important to go to infrared wavelengths, because when the light is coming from further and further, there is a wavelength expansion. So if this galaxy is emitting in UV, because it is so further away, we will receive that light in infrared. So if we have a telescope that has a filter that can catch infrared light, we will be able to see that galaxy. Otherwise, we won't be able to see that galaxy. So these are the two things. Okay. So then, but how do you know how far a particular galaxy is? So one of the tricks is this photometric redshift. How do you calculate how far a galaxy is through means how do you measure its redshift, and that is done through a dropout technique. So dropout technique is that the same galaxy is visible in more infrared filters, but as you go to more bluer filters, that galaxy disappears, because since that galaxy is very far away, its light has been red shifted to infrared filters. So although it will show in red filters, it will not show in blue filters. So these are the various filters of JWST, and this galaxy is when the universe was even less than 1 giga-year old. Means right now we are seeing universe when it's 14 giga-years. So when it was not even 1 giga-years, this is the galaxy, and we can see that for example, this one, if you see, it disappears as we go to this filter. So this gives you a first-hand understanding of how far this galaxy is. Then the next thing that is which is related to this is this Lyman break technique. So Lyman break, what happens is if the photons emitted by the galaxy are less than 0.1 micron or 1216 or 912 basically. So what happens is that those photons interact with the neutral hydrogen that is between the galaxy and us. So those photons never reach us. There's a Lyman scattering. The neutral hydrogen that they find on the way, they scatter it, they excite it, they ionize it, but overall those photons never reach us. So through this Lyman break, we can determine how far away that galaxy is. For example, here the Lyman break was supposed to happen here at 0.1 micron, but it has occurred at 1 micron. Like this is the spectrum of the galaxy, and the break has happened at 1 micron. So this tells you that this galaxy is at redshift 7. So this galaxy is when the universe was at 4 universe was, yeah, I think less than 1 giga year, when the universe was around 1 giga year old. So this is a technique through which you find out galaxies that are at higher redshift. Then another thing that you do is that you have fluxes of galaxies in various wavelengths, and then you create a spectra using various initial parameters. Means there's a galaxy, there are softwares that are able to create thousands and thousands of spectra by varying their initial mass function, their stellar mass, their how much stars they are forming, how much gas they have, how much dust they have, etc. So all by varying all those parameters, they create thousands and thousands of spectra. Then they redshift those spectra and try to match it with the fluxes that you have. So these red points are the fluxes for a particular galaxy. So here there are 4 galaxies. So these are their IDs, and then what you have done is that you have used that software to create spectra, and then you have redshifted those spectra to various redshift to see which spectra fits best. And then here you can see that there are 2 spectra that fit best. One is at redshift 9, one is at redshift 3. Then you see where the reduced chi-square is best, where it is 1, where, so you say that okay, this seems to be the best fit, this seems to be the redshift of the galaxy, and this is the best fit spectra. So if you don't have a spectrum, because spectroscopy is not that cheap, spectroscopy of each galaxy takes a lot of exposure time, lot of time, money and resources. So what you do is that you have photometric fluxes of thousands of galaxies, and you try to create their spectra and fit their spectra, and through that you get their spectra and get their other properties, means their star formation rate, stellar mass, their stellar properties. So this is another way in which it also determines how far the galaxy is. So here if redshift 10 is fitting much better than redshift 2, so you know that the galaxy is at redshift 10. Okay. Okay. So when you are able to do that kind of analysis, when you have thousands of galaxies in each mass bin, means with 10 raised power 10 solar mass, 10 raised power 9 solar mass, 10 raised power 8 solar mass. So you have thousands of galaxies at each redshift that are in different solar mass bins. Then you can place them and see if the overall mass of the galaxies has been increasing. And then there are models as to how this mass should have increased, if there was this hierarchical structure formation, if mergers happened, and at what rate mergers happened, at what redshift. So that from those models, there are predictions. And then there are observations, because you see thousands of galaxies in each mass bin at each redshift. So what happens when you have a better telescope, when you have a bigger telescope, then you are able to get more and more galaxies at each and every redshift in each and every mass bin. So this kind of analysis becomes more meaningful and more gives you more insight. Because if suppose I have only 10 galaxies here, I cannot say anything. So I should have all kinds of galaxies, and I should have them in large numbers at all redshift. So what we have found through that preliminary is that the mass of the galaxies increases as we reach the present epoch. It means when the universe formed to the point when we see it now, the masses of galaxies has increased. Then the next thing what you can see is the size of galaxies. But first you have to fix the luminosity, because size also depends on the luminosity of the galaxies. So you find so you select a particular luminosity bin, like 0.3 to 1 L star. So within that luminosity range, what has been the sizes of galaxies at redshift 7, at redshift 6, redshift 5, and through various softwares. And so then you are able to conclude, you are able to predict if the sizes have actually increased. And then there are several models that you can rule out or you can rule in through this kind of analysis. So what
Hello.
yeah.
Hello, madam. What is the meaning of redshift 7 or 10 like that number?
Okay, I'll tell you. So as I said that right now universe is 14 giga years old, 14 billion years old, and redshift is 0. As you go to younger and younger universe, redshift increases. Means when the universe was 7 billion years old, redshift was 1. How you can compute it is that you take a time upon 1 plus z. That you will give you a rough idea. But basically redshift, if redshift increases, you are going back in time. You are going when the universe was younger and younger. Okay. So now what the other thing that you can do other than measuring the mass of the galaxy, other than measuring their size, is that you can actually measure all their structural parameters if they are resolved enough. If so, what you can do is that this is the image of a galaxy. Okay. And then we have softwares. We do a lot of image analysis, and then we are able to create models that are best fit for that, such that when you subtract the model from the image, you get only sky. So overall you have modeled the galaxy and the residual is only sky, and your reduced chi-square is near 1. So, and then how do you see if it's consistent, if it's accurate? So here these black points is the intensity, how the intensity of the galaxy is actually changing, and these are the components that you have fit: a disk profile, a bulge profile, a spheroidal like profile, and the overall profile should match this profile that you observe from the galaxy. And then when you subtract the model profile and the observed profile, it should give you 0 residual. So that tells you that you have modeled the galaxy well. So this is so here this is how you have modeled it through two-dimensional image analysis. And here you have used those two-dimensional image analysis model and created profile, and this is the one-dimensional image profile. And so through this two different methods, you have confirmed that you have fitted the galaxy well, because these profiles have come from this model and this profile has come from this image. So overall, once you see the residual, so this is the way you can measure the structural parameters of a galaxy. Yeah. Then another way in which you can measure is that you don't assume any functional form, and that is the non-parametric measurements. So here these are parametric measurements because you are assuming that the bulge goes like this, the disk behaves in an exponential manner, it goes like this. So but when you are doing a non-parametric structural measurement, then you don't assume that there's any functional form to it, and you only count the counts. So for example, you take an image and you rotate that image. So there are these image reduction analysis softwares that easily do that. So just like if you have taken a camera and you have taken an image and then you rotate that, and then you subtract the rotated image from the original image, the residual that comes tells you that if that galaxy has been interacting, because that interaction is not going to be a uniform one. So that residual, how much flux is there, normalized flux, that tells you how asymmetric is the galaxy. If it is totally symmetric, then you should not get anything if you subtract the rotated image from the initial image. So these kind of analyses are non-parametric because you do not assume a functional form. Then how do you estimate the radius of a galaxy? So radius is that if how many counts are there in a annular disk and how many counts are inside that disk. So when that falls to 20%, let me show in that. So when that falls to 20%, so you know that when this count will fall to 0%. So you just see how the counts are falling, and that tells you that when this galaxy is going to end. So that is basically extrapolation. So that is also, then you are counting the counts, and then you can tell how concentrated the galaxy is. Means when was how much what is the radius that contains 20% of the light, what is the radius that contains 80% of the light. So like that also you can compute concentration or how dense the galaxy is from the center. So this is also a non-parametric measure, means you do not assume a functional form. So this is not biased by that I assume that there is going to be a disk, or there is going to be a spheroid, or how the shape of the galaxies are going to be. Okay, and then what tells you how consistent they are, how accurate they are. So let me just explain this thing. So this RB is the Petrosian radius. This radius, this is the total radius. This has been found in this non-parametric way. And this is a half-light radius. This has been found by fitting the model. So this has been found by counting the counts, and this has been found by fitting the model. And since their correlation shows, so all these dots are a galaxy, and their correlation shows that these two, both of them, have been measured accurately. And as we move from higher redshift to lower redshift, means when the universe was younger to now, we see that the total radius has become a larger multiple of the half-light radius. Means the galaxies have expanded from their outskirts. So this simple analysis shows that how galaxies have grown, and then it gives you a hint that maybe it has been that they have accreted matter to their periphery. So this so this also tells you how consistent or how accurate your parameters are, and also tells you how the galaxies have been evolving from a certain giga-year age of the universe to a certain how they have grown. Okay. Then now let me try to explain this diagram to you. It is very interesting if I am able to explain and you are able to understand. So this is the velocity dispersion, and higher this velocity dispersion parameter is, means more the galaxy is a spheroid like, and lesser this velocity dispersion is, means more this galaxy is disk like. So you can see that, so this is the velocity dispersion for various galaxies, and here galaxies have been placed according to their surface brightness and radius. Now if the galaxies are spheroidal, are elliptical, then we expect that they would follow the fundamental plane, means they would lie here. And when we put galaxies based on their velocity dispersion, they are totally coherent with how they would be placed if they were placed according to their structure. So basically what that tells you is that how structure and the velocity that has been measured are totally consistent. So what we have found to be a spheroidal through the surface brightness, through the radius, by placing it on the fundamental plane, is also spheroidal based on its velocity dispersion, and that which we found to be disk-like based on its placement according to its surface brightness and radius is also disk-like. Is also disk-like in terms of its velocity dispersion. It is less than 90. So that tells you how multiple methods lead to the same answer, that yes, this is the galaxy that you are saying it is, in terms of structure, in terms of their velocity, in terms of and other things also. And
Hello?
then
Madam, velocity dispersion means the rotation of the galaxy. Rotational speed.
Velocity dispersion means, so if the stars are rotating, then and they are confined to a disk, then the dispersion will not be there. Dispersion will be less. Dispersion will be less for a disk-like galaxy. But if the stars are in not confined to a disk, they are all over the plane, then that thing will have a higher velocity dispersion. Okay, so based on that, then we can classify the galaxies, and then since we have used multiple methods and we have shown them to be consistent, to be accurate, we can use them to classify galaxies based on their structure. And then what we have found is very interesting, that not just their velocity, not just their structure, their star formation properties also differ depending on their structure. So more disk-like, more spheroidal is the bulge of the galaxy, more is the mass of the galaxy, less is its star formation, and redder is its color. So it is quite interesting that how all the different properties of the galaxy, its structure, the velocity of the stars, and how much stars it is forming is all connected. So that tells you that there have been different processes, different physical mechanisms that have been responsible in creating certain kind of galaxies. So they have governed their structure also and their stellar properties also. Because we have divided based on structure, but we see that they are also divided based on their stellar mass, their star formation rate, and their color. So yeah, so that gives you another idea of how galaxies, we can understand they are, we can model them, we can understand them, and we can trace their growth, and we can tell something about their history. Okay, then one thing that helps is if you are able to fit the same galaxy in two wavelengths. So here this is the same galaxy and this is also the same galaxy, but this is in optical and this is in infrared. So if you take the galaxy and fit it in optical and fit it in infrared, then by how different it is in two wavelengths can tell you how redder is the bulge, how bluer is the disk, where is the star formation happening. And then here, like clumps, these small stellar clumps, they are visible in the optical, but they are not there in the infrared. So that tells you that these clumps are basically star forming, so they are emitting in optical, ultraviolet, but not in the infrared. So that kind of information gets revealed when you are able to see galaxies in two drastically different wavelengths. So that is also helped when you have telescopes that cater to the whole multi-wavelength range. Okay, then one thing that has been that is very interesting that we have found after studying galaxies since the universe began to now is that their star formation efficiency has reduced. Means they were forming a lot of stars when the universe was at redshift 2, when the universe was 3 gigayears old. But now they are not forming that much stars. So what has led to this fall in the star formation? This is called quenching, star formation quenching in galaxies. And there's a very dense research that goes on to understand that what has led to this drop in the star formation in galaxies. Why did they stop to form stars? So then the two answers that come to your mind is, first, that the fuel must have ended. So the gas in galaxies, gas through which they form stars must have ended, or the gas was there but their efficiency went low. Means the gas is there but the galaxy is just not forming stars. Just the gas is not cooling enough. The gas is not able to form stars. So it's the efficiency issue or the fuel issue. And as much research has been done, it has been found that it is not the fuel issue. Because as you see how much stars have formed over the years, when we reach here at redshift 0, when we reach the present age, the number density of stars has increased like this, but the fuel, the neutral hydrogen, has gone like this. So it has not decreased in proportion to the increase in the stellar mass density of galaxies. So what that shows is that fuel is there, but the fuel has played its role. Yes, fuel has decreased, but not to a level that it could explain this kind of drop in the star formation. So that means the star formation efficiency has also gone down. So then the question is that what has led to the fall in the star formation efficiency? If the gas is there, then why is the galaxy not forming stars out of it? So then there's a lot of research that goes on into that. Okay, so then one thing I would like to show you, which is very interesting, is that if you put galaxies according to their structure on the main sequence, means this is star formation rate, this is stellar mass. So all the galaxies that are placed here are supposed to be star forming, and all the galaxies that get placed here are supposed to be not star forming. And we see that this star formation has a very clear correlation with the structure of the galaxies. So all the disks, more than 90% of the disks get placed on the main sequence, means they are forming stars. And more than 90% of the spheroids get placed here, means they are quenched, they are not forming stars. So that shows a very clear, very distinct correlation of structure with the star formation that goes on inside galaxies. Note that each and every dot here is a galaxy. So when you analyze a lot of thousands and thousands of galaxies and you put them in these kind of plots, then they actually reveal a picture. Then they tell that how we have been talking amongst each other, how we have been growing, how different stages actually tell you the different growth stages of the galaxies. And also, if suppose, so there's this another structure parameter, and as the structure parameter goes towards this side, you can see that the galaxy becomes redder and redder, and here it's bluer, it's forming stars. So basically how so the other thing is that the galaxies seem to have gone from being a disk to becoming a spheroid. There has been a structural transformation, and there has been quenching, means the galaxies have stopped to form stars. So overall, there is an understanding that these two processes might have been through the same process, through the same trajectory. So as the structural transformation happened, quenching also happened. So the disk became spheroids and they stopped forming stars. So they pass through the Green Valley, and there's a lot of research on the Green Valley also. Okay, now let me tell you a little bit about dust. So all galaxies have dust, and dust is a very minuscule component, means less than 1% of the interstellar medium of the galaxies is in the form of dust. But dust reprocesses half of galaxy's stellar emission. So the importance of dust can be gauged from the fact that our own Milky Way would have been doubly bright in the optical if there was no dust present. So what dust does is that it takes the emission that has been in the optical and UV, and it reprocesses and emits in the infrared, in the mid-infrared and far infrared region. So what if you are trying to understand a galaxy, trying to study a galaxy, and you have no idea of how much it has emitted in the mid-infrared, in the far infrared, then you will grossly underestimate how much stars it has been forming, because it has been forming stars, but they are covered by they are not seen. That emission is not seen because that has been reprocessed by the dust. So you have to understand dust emission to get any kind of parameter for stars, any kind of stellar parameters. You can't get stellar mass, can't get star formation rate, unless you have the idea of how much dust has emitted in various wavelengths. So that is understood by the dust attenuation curves. So this is how much the light from a particular galaxy has got attenuated by dust in various wavelengths. So as expected, this is going to be higher in UV because dust acts most on the ultraviolet photons, and then as you go to higher and higher wavelength, the effect of dust just reduces. So if the galaxy is emitting in the infrared, dust will do nothing to it, it will just pass through. But if the galaxy is emitting in UV and optical, dust will scatter those photons, dust will reprocess them, and so you have to be able to model these curves accurately if you want any kind of stellar parameters for a particular galaxy. So this is another research that is very important, that you model the dust attenuation curves of galaxies. Then the last thing that I would like to tell you that is very recent is that it has been found that all the galaxies have a supermassive black hole in their center. And what is very astonishing is that the properties of this supermassive black hole that is at the center of a host galaxy, about 10 raised by 5 to 10 raised by 6 solar mass, in a galaxy that is 10 raised by 9, 10 solar mass. So the properties of the supermassive black hole and those of host galaxies are correlated. So why this is astonishing is, like, if you have a football and it is governing the properties of the whole stadium, and not just the whole stadium, I mean that in terms of the size, in terms of the size of the black hole and the size of the galaxy. So that is astonishing in the way that you want to understand that what are the processes through which the black hole is talking to the galaxy and the galaxy is talking back to the black hole. Why are these parameters correlated? This is, for example, this is the luminosity of the bulge of the galaxy. This is the mass of the supermassive black hole. So, and this is the velocity dispersion of the bulge. So, why those properties are connected? What have been the feedback mechanisms, and how these two have talked means what kind of feedback and through which way. And so that is another very interesting research that is going on right now in terms of understanding the growth of galaxies. And yes, it is most definite that the supermassive black holes have played a huge role in determining the properties of the galaxies. So what have been those ways? Okay, so then let me come to the last part, where I will, as I have been trying to explain you, that why do we need larger telescopes, why do we need to go deeper and deeper, is because that let's take this redshift range. Here the universe is like from 9 to 5 giga-years. So you are not able to see galaxies that are less bright than this. So what you have to do is you have to put a selection cut. You have to say that, okay, we will only look at galaxies that are brighter than redshift than absolute magnitude minus 19 or something. So so these kind of cuts have to be put, and then we don't know how the other galaxies would have been. We can't see less massive galaxies, we can't see low luminosity galaxies. So, but when we have larger and larger telescopes, we will be able to span the whole mass range, the whole luminosity range. So then in true terms, we will be able to see how they have evolved with each redshift. Yeah, so then we will be able to see how they have grown. So that's why we need telescopes and larger surveys. So like 15,000 square degrees, there's this Euclid-wide survey, there's another survey, LSST, 18,000 square degrees, basically spanning the whole sky in lot of wavelengths at better and better resolution to give you larger and larger number of galaxies at each epoch. So then you are able to do your analysis better. So let me just put that in clear terms. Like if you are going deeper, then what happens is that you will be able to see faint galaxies, less massive galaxies, low star forming galaxies, and all the galaxies at high redshift. And you will be able to see satellites. So satellites, there are all these small satellites that are surrounding a galaxy. They sometimes determine how that galaxy will evolve, how its size will increase, if it will go through mergers, through interactions, through what will happen. So we should be able to see the satellites. then we should be able to see the deep outskirts of the galaxies, because that is where most action happens, and that is basically faint, that is generally fainter. So you want to go deeper, and then you will be able to see interaction signatures, as I said, that the most action happens there. And then you will also be able to see inner features, like as I showed you earlier, that there are bars, there are spiral arms. But those kind of features, even if they are there, we need we need we need to be able to go deeper to be able to see those features. And then we should be able to track how the mass size has grown. We should be have a very large fraction of all kinds of galaxies at earlier redshift also. Okay, then if we have higher resolution, we will be able to see clumps, we will be able to distinguish the stellar populations, should be able to tell one component from the other. We should be able to separate overlapping neighboring sources. We should be able to separate diffuse asymmetric features. Then why do we want to go into the infrared? Is because we want to see red galaxies. Because if the galaxies have stopped forming stars, and galaxies mostly would emit in the infrared, because that is what most galaxies emit in, because of their low mass stars and mid mass stars emit in the infrared. So only then you will be able to track their mass distribution, because most of the stars from which contribute to the mass of the galaxy emit in the infrared. And we will be able to model the dust, because dust emits in the infrared, and then we will be able to get accurate stellar parameters. And of course, then only then we can see high redshift in UV and optical, because that gets red shifted to the infrared. And then of course we need spectroscopy, because that can identify, confirm, and so let me not go into that. Okay, and then let me just put this and end this talk. So what this is, that the various questions that we can answer for various kind of things. So all the things that I showed, there are several questions that remain unanswered, and they can be answered if there are people working on it and they have data that is of good quality, which JWST will provide, and all other surveys that are coming up. So we will be able to find if the disk formed during mergers or accretion. And so there are several questions that need to be answered, and they can be answered when we have better telescopes and we have dedicated people working towards that. So I end my talk here.
Yeah, Dr. Sonali, thank you very much for the very interesting and informative talk. So now it's time for question and answers. So we can take questions from the chat box, but before that, if participants, if you want to ask questions, you can directly unmute and go ahead. Or you can also raise a hand so that I can know if anyone wants to ask a question. So you may raise a hand if you, Anurag Bhaisare. So you may unmute and ask.
Yes, I think I'm audible.
Yes, you are audible.
Solani ma'am, you have given us such a nice talk. Thank you for that. And I have put my question on the chat box also, but then also I would like to ask that what filters you have used in the structural parameter of the galaxy you have shown in your PPT.
So there are several filters. So like if there's this optical, like a human eye can see from 0.4 to 0.7, right? Micron. So there will be several filters that are put that have a certain band pass. Like there will be a U, V, G, I, G, R, I, Z filter based on what wavelength there is. And there are, so in that filter, it is catching the light. So suppose you put a green glass in front of you, you will be only able to, green glass in front of an object, you will only be able to get those green light. So those kind of filters are put, and yes, we have, there are several filters that are in the optical waveband, then in the infrared waveband. So does that answer your question?
Actually, I want to ask in specifically code. In coding, you must be putting is your that the structural data you have shown, it is related to coding.
So we use a software to fit models, and we take a galaxy in a particular filter in which it is best viewed. And sometimes we uh, stack galaxies in different filters to get a better view of the galaxy.
Okay.
Any other
Hello.
participants?
Hello.
Yes.
Hello, am I audible?
Yes.
Madam, what is red shift number and blue shift number?
So, Dr. Sonali, the participant is asking what is redshift number and blue shift number.
Blue shift? No, there is no blue shift number. It's just that we don't talk in terms of giga years. We don't talk in terms of the age of the universe. We talk in terms of redshift. Redshift is totally related to the age of the universe. So as I said, that if the redshift is 1, the universe was half the age it is now, because you take the total age and divide it by 1 plus z. So that will give you the time in which we are talking about. But it's just that the astronomers talk in terms of redshift of of an epoch, and that refers to what time it was at that time, like universe was how old.
That means if red shift number is more, then the universe is younger. The galaxy is
No, redshift now is 0. Redshift can be anything. Redshift can be 1100 also, 1200 also. Right now it's 0. Age is 13.7, right? So age is more than, yes, we are older. If suppose somebody tells that the age of the universe is 21 giga years, then 21 giga years have passed since Big Bang. But if it's 13.7, then 13.7 giga years have passed since Big Bang.
Dr. Sonali, let us take some
redshift
questions. Okay, I think your question has been answered. Let us take some more questions from the chat box. So Ansel wants to ask, what is R chi-square?
What is?
RCHI2 that you have used.
Oh, reduced chi-square.
Yeah.
Oh, this is how you fit a model. This is how you see that what is the difference for each pixel, and you try to find that what is the best fit for that model given the difference that is allowed for per pixel, given the noise that is there in each pixel. So based on that, what is the best fit for a galaxy? So that is reduced chi-square. That is done whenever you fit a model to a data. Whenever you fit things, that is a statistical measure.
Bharati wants to ask, ma'am, how much is the theoretical calculation about galaxy accurate?
So that is what we try to find out. We are observational analysis. We have this data, and there are several models. And when the data does not conform to a model, then that model has to be replaced. That model has to be rectified. So that is how through this observational analysis you are able to rule out or rule in a model that yes, this model looks correct in terms of how the galaxies would have formed, would have evolved, and this model does not look correct. So that is in terms of you have your theoretical models have to match with the observational data that gets available with telescopes.
Then Manisha Jha has asked a question, but it is not clear to me. What does y-axis indicate and why it have a negative sign? So she might, Manisha, you may unmute.
So negative must be absolute magnitude. See, okay. I think so. The problem is that we talk in terms of magnitude, and lower the magnitude, brighter is a galaxy.
Okay.
So like through naked eye you can see apparent magnitude of some 6.5, but when a galaxy when anything has a magnitude, like you will be able to see Sirius, etc., some stars, because they have a magnitude less than that, 1 or 2. But if but here magnitudes that we are talking about is 22, 23, 24. So those kind of magnitudes you need telescopes. So higher is the magnitude, more is the magnitude number, less bright is the galaxy. 5 magnitude difference means that object is 100 times less bright. Suppose my magnitude is 5 and some other galaxy's magnitude is 10, then that galaxy is 100 times less bright than this galaxy, than my galaxy.
Dr. Sonali, there are a few more questions. Shall we take them up? You can yourself see in the chat box. You may choose some questions to answer yourself from the chat box.
Can we? What could be the reason that more supermassive black hole is present in the center of the? So, what could be the reason that supermassive black hole is present in the center of the galaxy? We don't know. Maybe they got formed when the galaxy got formed. Maybe they are a product of when the merger happened when in the galaxy formation process. Maybe they formed at that time. So that is still debatable. And if they have grown alongside, means as the galaxy has grown, the supermassive black hole has also grown. So those kind of questions we want to answer, and yes, that is something that we would like to know for ourselves too. Okay. Can we see the galaxies with naked eye in the galaxies? If you are in the south, then you can see this LMC, SMC. But with the kind of pollution that is here, I don't think you will be happy if you can see stars. What difference compared to HST? Okay, what difference in technology has been brought about in the JWST compared to HST apart from increased aperture? So apart from increased aperture, the most important thing is that it looks into the infrared. HST, even when it was wide field camera 3 that was put in 2009, it was able to go till 2 micron. But with at JWST, you go till 23, 24 micron with a very good resolution, and then even higher wavelengths at a lesser resolution. But the main thing is that it will be able to go into the infrared, which, as I said, is infrared is most important if you want to see high redshift galaxies, if you want to model the dust best, if you want to. So, as I said, that if you want to see galaxies that are quenched, so that is most important. That JWST, other than the increased aperture, it goes into it sees the infrared of it sees the universe in the infrared wavelengths. How you differentiate galactics and black holes?
Dr. Sonali, maybe since the other speaker is waiting, maybe you can. What do you feel? You can answer these questions in the chat box itself.
Okay. Yes, I'll do that.
So, and thank you, the audience, also for asking your questions. So I thank Dr. Sonali very much for your very interesting lecture, and the participants also, they have asked a lot of questions. We now move on to the next talk by Dr. Aruberi. So Aru, are you there?
Hi, yes, I'm there, Biplov. Thanks.
Yeah, thanks. So let me give a introduction to Dr. Aruberi. So Dr. Aruberi is an inspired faculty of physics from the Indian Institute of Science Education and Research, Mohali. She completed her PhD from IIT Ropar in 2016. Before joining IISER Mohali, Dr. Berry was employed as a consultant to the LEXPC instrument on board AstroSat at Raman Research Institute, Bangalore, India in 2016. After that, from 2016 to 2018, Dr. Berry worked as a postdoctoral research fellow, Royal Society, SCRB, Newton International Fellow at the University of Southampton, UK. Dr. Aruberi is an active member of the International Astronomical Union. Her research areas include high-energy astrophysics, X-ray astronomy, and X-ray binaries, neutron stars, and black holes. She is also interested in astronomy education, communicating astronomy with the public, and astronomy outreach. Today, she will deliver her talk on probing regions of strong gravity by mapping accreting neutron stars and black hole. So, Dr. Berry, please go ahead with your talk.
Sure. Thanks so much, Poplar, for a nice introduction. Thanks, everyone who are there for my talk. And thanks to all the organizers for inviting me to give this talk. And I apologize in the beginning if my energy levels are low. I'm not well, so I'm on medication. So it could be possible that my voice may not be always consistent. But let me know if there is any technical issue or I'm not equally audible to everyone. So with this, I will begin with my talk, probing regions of strong gravity by mapping accreting neutron stars and black holes. So in this talk, we'll be talking about neutron stars and black hole systems in a binary systems. So might all have heard a lot about black holes and neutron stars. So to kickstart my talk, let's start from the life of the star. So we all know that just like human being, stars also live and die. So end products of the stars is results of that end products of the star is either a neutron star or a black hole. So this artist impression basically shows you the beginning of the star, which is starting from the protostar, from star forming regions. And then if depending upon the mass of the star, the fate of the star is being decided. So if your a star, which is very massive star, then it results in a black hole. And if it is, it's like a middle or less massive star of less than 3 solar mass of star, then it may also end as a neutron star. And if it's like and then there is a evolution phases of how the stars evolve. So for example, if this protostar leads to a sun-like star and it undergoes a red giant phase, then it basically explodes and forms a planetary nebula, and which can also result in a white dwarfs. So white dwarf, neutron stars, and black hole all can exist in a binary system. This is another artist impression of showing we might all have heard about hydrostatic equilibrium in a star. So what exactly it is? So the gravitational pull of the star is being balanced by the radiation pressure, which is being generated by the fusion reactions which are going inside the star. So those fusion reactions generates energies, and that energy basically balances the gravity of the star. So once, for the period when this balance is being maintained, the star is basically happily living. And as the nuclear fuel inside the star depletes, and then basically it undergoes an implosion process because it collapses under its own gravity. Now it does not have a radiation pressure to sustain or balance the gravity with its radiation pressure. Because there's no nuclear fuel available in the star, and hence it undergoes that implosion and then finally that explosion process, which really becomes a runaway process, which is also known as supernova explosion, and hence result in our black hole or a neutron stars. So this is a short video which will explain.
Have you ever wondered how a star dies? Or better yet, what happens while it's dying? Almost always, the answer: a supernova. Star classification is pretty complex stuff. There are tons of different kinds of stars. Blue giants, white dwarfs, red giants, red supergiants. For example, our sun is considered to be a type G2V yellow dwarf main sequence star. Yeah, don't even worry about what that means. Plus, each type of star has a different size, brightness, temperature, and lots of other things. Pretty much all stars are unbelievably large. Even our own sun could fit 1 million planet Earths inside of it, and it's considered to be an average or even small star as far as the rest of the universe is concerned. This giant size causes tremendous gravity that's constantly trying to come crashing in on the star. And this pushes everything that the star is made of down towards the core. The pressure and density inside of a star would be truly unimaginable, like being millions of miles deep in the ocean, times a million. Even microscopic atoms, the very building blocks of our universe, can't stand this pressure. Warning, we're about to get a little scientific, but it shouldn't be too bad. And if you don't care, take a 20-second power nap starting now. Hydrogen, the most simple and common atom in the universe, is everywhere, especially inside of stars. The tremendous pressure inside of the star is so strong that it strips hydrogen's electrons, leaving only a bare nucleus. And under this crazy pressure, the bare nucleus of hydrogen combines with other bare nuclei, fusing together, making heavier elements like helium or oxygen. In physics, this is known as nuclear fusion. And now the new heavier elements have tons of extra energy they're not used to, and they're not exactly crazy about this. So they release or emit the energy as radiation. This radiation spills into space, and some of it becomes the very light that heats planet Earth. Not to mention, this powerful energy flowing outward prevents the star's gravity from crushing it. A star is constantly pushing out with nuclear energy and trying to come crashing in with gravity. And this delicate gravity-nuclear balance is how stars stay alive. But eventually, like a car running out of gas, the star runs out of atoms to fuse. But there's nothing to stop gravity. As a result, everything that the star is made of comes crashing into the core, and all of this matter stuffed into a small place becomes a nuclear time bomb. All of the matter and radiation blasts out into the universe in a catastrophic explosion known as a supernova. Every single element that we know on planet Earth came from exploding stars. The nitrogen in Earth's protective atmosphere, the calcium in your explosion. Type 2 supernovas occur.
So here in this video, we basically saw what is supernova explosion and how does it take place and lead to the formation of a black holes. So now talking more about black holes after they are formed from the supernova explosion. So there are types of black holes. Some are known as stellar mass black holes. There are supermassive black holes, which in the previous talks you've already heard about. Like they have masses of millions to billions times that of the sun. And for stellar mass black holes, the mass of the black hole is around 5 to 20 times the mass of the sun. However, now there is a beginning of the discovery of intermediate mass black holes as well. However, the evidence of that intermediate mass black holes is not always very convincing, but the mass range is of 100 million times that of the sun. So in this talk, we'll be focusing about stellar mass black holes, which exist in a binary system. So question to everyone in the audience. So is it possible to hunt a black hole in this image? I would like to see some raised hands if they are able to identify a black hole. Are there?
So Anurag has raised his hand.
So yes, Anurag, what do you think? I mean, I will not be able to see, but you can speak up if it's possible.
Yes, sure, ma'am. With this image, first we can find the evidence of any gravitational lensing, or we can use any software, and we can also use any Python coding with the help of any filters or something. We can see is there any gravitational lensing or not. If any gravitational lensing exists, then the black hole might be there.
Very good, Anurag. Excellent answer. I agree that because these are strong gravity objects, so they are basically having effect on the surrounding medium, which is basically having warps in the, or basically distorting your fabric, which is a space-time fabric here in the case of universe. So we can identify the presence of a black hole in a universe from these direct measurements like gravitational lensing, or can you think about some other ways of, or I mean in this image with the naked eye, can you think that we can really identify a black hole if we are not really relying upon any observational features as such? I mean, you are not like relying upon sophisticated ways of identifying a black hole, but just if I've given you this image, can you really say that there's a black hole here in this image?
So, Dr. Kamal Jyoti,
by finding the light from quasars.
Yeah, but then again, for that you need some sort of observations. But that is true. It's very much related to what Anurag mentioned. Yeah. So the direct answer to this question would be no. We cannot really see this image and say there exists a black hole. They may exist or may not exist, but just looking or staring at this image with your bare eyes, you cannot really tell whether there exists a black hole. So of course you can rely upon other observational evidences, which you all have talked about. Another way of identifying the presence of a black hole, if there exist binary systems, and if we have observations, we can actually probe the presence of a black hole in that system. So that is another indirect way of hunting black holes in the system, if we hunt for these hidden monsters. So what are these hidden monsters? These are exabinary systems. And in these systems, what happens is a companion star, which is placed here, it basically gives off its matter to the companion star, the compact object, which is a black hole or a neutron star, sitting somewhere at the center of this image. Because these are strong gravity objects, so they have larger gravitational pull. So they basically accrete matter from the companion star, and because they have huge angular momentum, the matter cannot directly impinge onto the compact object. So what it does is it leads to the formation of an angular disk, which is called an accretion disk, because this process of mass transfer is known as accretion. So the disk which is formed around the black hole is known as accretion disk, and that leads to this leads to the gravitational energy release, which we observe in the form of electromagnetic waves. And since these objects are predominantly emitting in X-rays, these systems are known as exabinary systems. But that doesn't mean that they are only emitting in X-ray band. They do have emission in other wave band. So if you really want to understand a comprehensive picture of these systems, like different emission and physical processes which are causing the changes in the accretion and so on, we need a multi-wavelength study of these systems. For example, in this image itself, you see a jet being labeled, and this jet is basically observed in radio band. So in the same way, when we say accretion disk, these are annular disk like radii, which is formed around the compact object, and inner part, which is closer to the compact object, which is a black hole, is emitting in X-rays because it's extremely hot. The temperatures are of the order of 10⁶ to 10⁷ Kelvin, which basically lies in the X-ray range. And so inner part of the accretion disk is extremely hot, illuminating in X-ray band. But as we move away from the compact object, goes towards the outer disk, they are more emitting, or they becomes cooler, and then they emit in optical band as well. So this is an artist image impression, which basically shows you how the accretion is going on with this system. So what is the motivation of understanding or studying these exabinary systems? So of course, there are other ways also of testing general relativity, which you have mentioned before. Like we can look or probe for signatures of gravitational lensing. We can also directly measure, because now we have gravitational wave detectors, we can also look for signatures of gravitational waves. But we also know that gravitational radiation, or measuring gravitational radiation, because these are weak forces, it becomes immensely difficult also to really detect those signals over your noise. But these systems are very efficient systems of accretion, so we can get higher signal to noise ratio in the case of very bright systems, and hence becomes very efficient way of also testing general relativity. So far, what scientists have probed or looked for the signatures of, or finding whether the general relativity proposed by Einstein is correct or not. So far it is flying in colors, which means Einstein's general theory of relativity is being satisfied. But still, astronomers are probing regions closer and closer to the black holes. to understand the dynamics around the black hole systems. Because these binary systems are the smaller systems, we can basically mass scale them. So basically, when we understand the evolution of the universe in the overall, like we understand that supermassive black holes are very much responsible for the evolution of our galaxies, of our universe, and so on. So basically, if we are able to understand how the black holes in a smaller range is affecting the regions around them, we can basically do that mass scaling and hence be able to understand the effect of that strong gravity from that supermassive black hole. So basically, this mass scaling thing, and these systems being smaller, they tend to do show variability and changes in the pattern in the time scales, which are way smaller compared to the evolution or the variability time scales observed in supermassive black holes. So basically, in that way, we can also get a big picture by studying these small systems. So this is an example which I was talking about earlier, like we can understand the variability because if you look upon, so this is an example from the real data, which is like observational data in the X-ray band, which we have observed. So on the y-axis, which is in all the panels, the y-axis is basically giving you the count rate or the intensity variation. And on the time, on the x-axis, we had the time. So time is in kiloseconds. So each panel or each box here is basically showing a single observation being made by an observatory and giving us the information how the count rate was varying over time. So as you can see, for each panel, you have observed different patterns. Some are showing large kings, some are showing like some sort of random variability, some are very much sort of quasi-periodic behavior is being observed in certain images and so on. So these observations were taken for one single object and during at different epochs. And so when we observe these dynamic behavior around the black holes, one can also probe what is the frequency, because you can do the Fourier transform of these light curves, because we call that intensity versus time as light curves. In a scientific community, we can call that as light curve. So you can basically do the time series or Fourier transform of your time series, and you can understand the frequency and so on, which can give us clues about how the dynamics around the black hole is being changed over time or is changing over time. Now I mentioned that each box is an observation taken at one instance. So this is like a light curve from an all sky monitor, which is different all sky monitors like Maxi and BAT, and for 2 different years, 2011 and 2013. So each data point, which is shown in red or black data point, is basically a zoomed in version of this. So this is a zoomed in version of each data point shown here. So which means if you look at upon the y-axis again, the intensity is measured, which is in units of crab, because crab is being considered as the standard candle. And on the x-axis again, it is time, but now not in kiloseconds, but in days. So which means it's like a years long data. So if you look at this light curve, basically you see that for several days or even months, it showed no activity in X-rays. And mind you, we are talking about X-ray binaries, and this talk is more focused on X-rays electromagnetic bands. So this is X-ray light curve. And we see no variation or no intensity so for several months, and then suddenly there was a shoot up in the count rate, and then you see a large variation in the count rate, which is like going to the entire outburst. And if we do this pointed observations, which is like each red data point, so we propose for observations for each during each day for this bright outburst, we can basically probe into the variability around the black hole. So what when the accretion is going on around the black hole, how the dynamics around the black hole is being changed, or what are the signatures in the changes in the space time around the black hole during these events. So I mentioned about the Fourier transform of your time series. So this is an example which is basically showing the power density spectrum of one system, but this is not a black hole system, it's a neutron star system. Power density spectrum, this I know for sure because I know from which observation we have this periodogram. But similar periodogram can also be done for black hole binary systems. So this power density spectrum is being generated, and then suddenly you see a sharp feature in the power density spectrum at very higher frequencies. So the frequency, if you just zoom in into this portion of the frequency range, you get a frequency around 820 or 830 kilohertz, which is very fast spinning system or a fast spinning neutron star system. So as we are closer to the compact object, which can be a neutron star or a black hole, you expect higher frequencies. And as you move away from the black holes or the neutron star systems, your frequency should basically decrease. So understanding or probing into such features can give us the information about the variability timescales and closer to the black hole systems. So we talked about X-rays observations, but then the question arises, how do we observe X-rays? And we all know that unlike other wavebands like optical and radio, so X-rays are opaque to our atmosphere. So basically we have to send satellites beyond our Earth's atmosphere. And those satellites basically have detectors on board, which are helpful us in getting us information in X-rays. So these are some example satellites which are currently or are up in the sky, which are giving us excellent quality data. So for example, this image on the top left is of XMM Newton, and this is this is a ESA mission, which is basically working in a band of 0.3 to 12 kV band. And this is very much useful in doing high resolution spectroscopy and even fast timing to some extent, and also getting us information about spectroscopy and so on. It has both grating spectrometers and also CCD cameras on board, which can allow us to probe into the physical processes by understanding the X spectrum of the systems. On the top right, we have a new star, which is the first hard X-ray imaging instrument. Before 2012, there was no hard X-ray imaging instrument. They were like proportional counters, scintillator counters, which can allow us to probe into the X-ray. So just to make it clear to the audience, if you are not familiar with the terminology of soft and hard X-rays. In X-rays band, first of all, unlike other wavebands like optical or radio, we're not talking in terms of wavelength. We talk in terms of keV, which is energies. So when I say soft X-rays basically means the energies which are below 10 kV, and any photon which has energy above 10 kV is considered as hard X-rays. So just be clear in your mind, when I say soft X-rays, it means any energies which are below 10 kV. But if I'm talking about hard X-rays, it basically means energies beyond 10 kV. So beyond 10 kV, there was no imaging instrument before 2012, and NuSTAR was the first instrument flown. And it's doing really excellent in understanding the emission in the hard X-ray band. Then on the bottom, we also have Indian mission, which is a first multi-wavelength mission by ISRO, and which is known as AstroSat. And AstroSat is doing excellent in terms of understanding the multi-wavelength behavior of X-ray binary systems. And in this image, we have marked all the detectors on board AstroSat. So the red boxes are the proportional counters, LAX-PC counters, large area X-ray proportional counters on board. And this instrument is really great in understanding the variabilities, which I was talking about to you earlier. To probe into those variabilities, we need high time resolution. We need larger collecting area, because we require larger number of photons to be collected in these proportional counters to be able to have larger statistics, so that your signal is way higher than your noise. So and also the time resolution plays an important role, because if you have when we are talking about these variabilities which we saw in the previous slide, those variabilities can really scale to all the way from milliseconds to kilohertz of frequency range. Uh, so uh, uh, so basically spreading all the way to a very fast variability like kilohertz variability, because we saw that 850 hertz frequency in the power density spectrum. Improving on those fast variabilities in the systems, we require high time resolution, so that we have large number of photons being collected at a very fast rate, so that we are able to get those signals being detected in our power density spectrum. Otherwise, they will be just smeared out in our noise. So then in the bottom left, we also have another NASA mission, which is RXT. So the light curves which I showed you earlier were from RXT mission. It also had a proportional counter, which was doing similarly to LAX-PC. And in AstroSat, we also, as I talked about, other payloads, like we have SXT, which is basically covering 0.3 to 7 kV band in X-ray. And then we have CZTI, which is again a hard X-ray telescope, a hard X-ray detector on board. And then this hard X-ray detector works from 15 to 200 kV band, really giving a very wide range coverage. And what makes it multi-wave band is also UV on board, which is excellent for observing in optical and the UV band. So collectively, it is becoming a multi-wavelength satellite, and also having SSM on board is a all-sky monitor sort of thing, which was on RXT, which was a NASA mission being launched in 1995 and was lasted until 2012. So this SSM can be very useful in observing the outburst which we saw before in the image. So detecting those transients in the sky, SSM is very helpful because if there is any such change in the illumination in X-rays, one can do the pointed observations with AstroSat to look at variability in a fast or short time scales, basically, because you can propose for observations or monitoring observations to look at how the evolution of your accretion takes place throughout the outburst, and hence how the variability is being changed over time. So I just did talk about that it's predominantly emitting an excess, but then yes, to understand the dynamics of the system, we basically required the multi-wavelength study of these systems. Because with X-rays, you can basically probe regions close to the black holes, but then that is resultant of the incoming matter. But when we are talking about accretion, it's not really a conservative process. You also lose energy and also being lost in form of winds. It can be form of the jets. So basically that outflows from these systems are also required to be studied together simultaneously at say. So for example, if there is an outburst going on in the system, and if you have a pointed observation done only with X-rays, what you are probing is the regions which are closest to the compact object. But what about whether there was any outflow in the system or no? What is the origin of your uh, hot electrons around the black holes and so on? So, I mean, there are several important questions which are mysterious to us unless you probe into that system in a multi-wavelength fashion. So I discussed briefly that outer regions of your accretion disk can give us information about in the optical band. In the same way, if you look at the jets from these systems, you can understand in the radio band how these jets are basically, and the mechanism behind these jets is really an open question, nobody knows. Then you can also have optical emission from the base of the jets and so on. So studying the system comprehensively is always a challenge. The challenge is because we are talking about coordinating different observatories working in different wavebands at the same time. So which means you require a large team efforts to really observe a particular system at the same instance, which is a challenge, but now it's been possible by the network of the worldwide community, which are having different observatories, control, and so on. They are trying to do this multi-wavelength observation, and hence it is really going into in a way which we really would like to see in the future, or are being also being seeing in the present at currently. So this is one example, which is excellent example, a very recent study done by us. This example is from Coral Santana in 2013, which was published in Science. And what you observe here is the optical light curves, not X-ray light curves. So if you see on the y-axis, we have R band magnitude. And these are the light curves of a black hole candidate X-ray transient. And if you zoom in into these light curves, what you observe is sharp dips in the light curves. And you further zoom it, you really see a broader dips and so on. And if you do the Fourier transform of these optical light curves, what you see is sharp peaks being observed in the periodogram. And these observations are being taken at different dates. So you can basically make an analogy to the X-ray light curves, which are shown you earlier. So each red or black data points from the outburst were zoomed in by pointed observation, and in the pointed observation you observe the variability in the X-ray light curves. In the same way, now these observations are done in optical band, and when you do the Fourier transform of these optical light curves during different dates, you see a frequency being observed in the periodogram, but that frequency of the QPO, or the quasi-periodic oscillation, we call it as in scientific term, these frequency of these features or the quasi-periodic oscillations do vary with time. And on the bottom panel, we basically see the time on the y-axis, and on the x-axis, it shows the frequency. And you clearly see that frequency was basically decreasing with time. So if you see start in the beginning at like close to the start of the outburst, you see a very high frequency, and as you go towards the declining phase of the outburst, you see basically a smaller frequency being observed in this. So basically it shows the frequency evolution during the outburst. And if you remember my description of the previous image, when I mentioned that if you're closer to the compact object, you expect it to be spinning faster, and if you're going away from the black hole, it is expected to spin slower. So then, based upon this observational study in the optical band, what Coral Santana proposed was this simulations showing what could be the origin of these optical dips observed in the light curves. And what they found was there could be, proposed was, there could be an obscuring structure in the inner part of the accretion disk during the start of the black hole. And this obscuring structure is causing the dips. And because it is closer to the compact object during the beginning of the outburst, it is at a higher frequency. And as the outburst is declining, this obscuring structure, which is shown in this image, is basically moving outwards. So when it is moving outwards, it is at a lower frequency. So this obscuring structure is something similar to known torus, which is being observed in supermassive black holes, in aging systems, heavily obscured aging systems. So that torus may exist in the accretion disk of this peculiar X-ray transient. So, yeah. So that showed us some power of probing into the regions of the strong gravity system in a multi-wavelength band. So X-ray is not always sufficient to understand X-ray binary systems. You also need observations in different wavebands to get more comprehensive picture of those systems. Now, with the current state-of-art instruments like IXP, which is a polarization mission, this is a very important mission since advent of X-ray astronomy. So X-ray polarization basically adds on. So with X-ray astronomy done till date, what we have is like timing, imaging, spectroscopy, information. But when we add X-ray polarization measurements, we are basically adding two extra dimensions to our observations to get clues about the dynamics around these compact objects. So what are these two extra dimensions? One is polarization, what is the degree of polarization, and what is the angle of polarization. So basically you can imagine it as like electric field oscillations, and how they are inclined with the light rays and so on is called angle of polarization, and how the extent of the electric field vector, polarization vector being inclined to the light rays can give us the measure of the degree of polarization. Unlike optical polarization, which basically is being like what our Polaroid glasses do, in X-ray it cannot be done because X-rays, as you know, there does not exist any filter to access. So what astronomers are doing is instead measuring the polarization of all the incoming light and seeing how much is the light being scattered and how much is being reflected, because X-ray can be polarized only due to the reflected component and the component which is parallel to the light rays. So any scattered beam will be filtered out if we are talking about the optical Polaroid. But then since there cannot exist any such X-ray glass, what we measure is how much is the component being scattered and the reflected, which will give us the measure of degree of polarization, and hence we can get some extra dimensions, which can also help us in understanding, give us more direct clues about how the dynamics around this compact object is behaving, and what physical processes and how those physical processes, what is the geometry of accretion around these objects. This will become more clearer from this image. For example, we talked about jet in the X-ray binary system. Then what is corona? So corona is basically the hard X-ray component which is coming in the X-ray band, and this is nothing but hot electrons which are existing around the compact object. So these hot electrons are known as corona, and then they can also have different shapes. And shape of this corona is really unknown. We do not know what is the shape of corona. So multi-wave band study can, of course, give us more information about how the outflow and the inflow is taking place. But with X-ray polarization, if the X-ray polarization is also varying as a function of the radii, like if its inner part of the accretion disk is highly polarized compared to the outer part of the accretion disk and so on, we can also probe into how the geometry around this compact object is changing with radii or distance from the compact object. So the time-dependent X-ray polarization measurements can also give us a clue about the changes in the accretion geometry. And there have been some X-ray polarimeters. In 1975, OSO-8 was the first being launched. This was like last X-ray polarimeter which was being launched in 1975. Since 1975 until 2021, there have been no X-ray polarization measurements. So today it's a really ripe time where we also have extra dimensions to probe the regions of strong gravity. So there are different principles being applied for the detectors on board. So for example, OSO-8 was based upon Bragg's reflection, and they were also working in different energy bands Like for example, OSO 8 was working from 2.6 to 5.2 kV band. And then now currently in 2012, IXP, which is working on this photoelectric polarization measurements, like it has a gem detector on board. So basically it is based upon the electron tracks which are being formed by the interaction, because it has a gas counter, and we all know that when the X-ray interacts with that gas, it basically generates electron and ion, and that Auger electron basically creates tracks in that detector. And the interaction, so the basically how much is the interaction, how many charge particles are being created are directly responsible to the signal which we observed in here in each time being, and is also being denoted by this like size of the pixels basically shown in this image. So we basically track the signals being created during this interaction process, which can give us the information or the measure of your polarization, which is being taken place by the interaction of your incoming X-ray with the gas in the gem detector. And then we also have Indian mission to be launched very soon this year, which is known as POLIX, Onboard Exposat, and this is based upon Thomson exopolarimetry. So unlike IXP, which works in 3 to 8 kV band, this Thomson exopolarimeter will cover 8 to 30 kV band energy range, and it is based upon Thomson polarization principle. So it has proportional counters on board, and it has all like two shapes of proportional counters. One is cylindrical and other are rectangular, which are basically surrounding the cylindrical detectors which are at the center, and the incoming photon will hit this cylindrical detector which is at the center, which is also shown here in the pink, and these are like side proportional counters, the rectangular proportional counters. And by rotating the plane of this detector, you can basically measure the extent or the degree of polarization of the incoming X-rays. And with this mechanism, you can basically measure the polarization or the degree of polarization of these incoming X-rays. But it works in a complementary energy range. And with IXP and Exposat to be launched very soon, we will be able to have a very wide coverage of X-ray polarization measurements, and that is very useful, because if you remember, I talked about that the inner part of the accretion disk can be extremely hot, then outer can be colder, and so on. So which means if you are combining the powers of the two complementary energy range, we can basically cover the larger part of the accretion disk around those black holes and so on. We can get more information about how the X-ray polarization is basically behaving as a function of the radii. So to give you some illustration, in the case of black hole binary systems or X-ray binary systems in general, we talk about hard state and soft state. So these states are being classified based upon the spectral evolution in these systems. So in the case of hard X-ray spectral state, what we expect is the accretion rate is lower, which means the accretion disk, which is formed due to accretion, is basically away from the black hole systems, and you have larger hard X-ray photons coming from the strong electrons or the hot electrons which are existing close to the black holes. So this strong corona is basically what is hot electron systems, which is existing around this compact object, leading to the hard X-ray emission in the hard X-ray state. And then you also have a soft spectral state, basically, which means if you have a black hole, you have a higher accretion rate, your accretion disk is now moving closer to the black hole, and you expect to have also thermal emission coming from the inner part of the accretion disk. And that, which can be taken care by the black body emission or the disk black body, and you also have some contribution from the hot electrons or the corona, which exist in these systems. So you classify based upon the spectral X-ray spectral study, whether the object is in your soft state or a hard state. And telling you more about the power of multi-wavelength and X-ray polarization together is very recent example shown here by observations which were done with IXP of a black hole candidate, not black hole candidate, the confirmed black hole system, which is Cygnus X1. And in this, Cygnus X1 was observed by IXP in its hard spectral state when you have corona emission being dominating, because you have hot electrons around the black hole. And during this X-ray polarization measurements, what these authors found, basically the degree of X-ray polarization was aligning with the, so this orange is like X-ray polarization measurements, which is like a northeast direction here. And these contours are the radio emission, which is the jets which were observed during this observation in the hard X-ray spectral state of the system. And you see in this image, basically your radio jets are aligning well with your X-ray polarization measurements or degree of X-ray polarization. So based upon this measurements, one can try to see which theoretical models one can accept or refute, or what are observations are basically supporting in terms of theoretical confirmation, and what models we are not able to accept based upon our observations. So for this particular system, all the models which are assuming the lamppost, because lamppost model is some sort of geometry which is being proposed by astronomers for the corona. So it's like a all the hot electrons are along the spin axis of the black hole. So this is in a very simple way of describing a lamppost model. But when you observe the X-ray polarization and see the degree of X-ray polarization aligning with the radio jets, this model is no longer valid. And what you expect is like an extended emission, not coming from this, not coming by aligning your hot electrons along the spin axis, but it is perpendicular to your radio jets and so on. And the hot electrons are way above the black hole system. So there's this extended model being supported by the observations which were done both in X-ray band and also with the radio. So combining all these diagnostic tools, one can get a more confirmed signatures or probes into the accretion geometry of these systems, and that is power of having such observations in the future and also in the present. So with this I will end my talk, and thanks everyone for your attention.
Thank you, Dr. Aruberi, for such a nice presentation. We'll now move on to the question and answer session. There are a couple of questions in the chat box. Maybe we can take them up one by one. Okay, Rishabh Singh has raised a hand. You may unmute and ask your question, Rishabh.
Hello, am I audible?
Yes,
you are.
Yeah. Yes. Will they check the jets with different orientation of the accretion disk?
Rishabh, can you be a bit louder, because your I think the quality of the sound is not good.
Okay. So hello. And there will be
I suggest you please type your question in the chat box. We will come to your question. Okay. Dr. Kamal Jyoti, do you want to ask your question? Dr. Kamal Jyoti?
Yes, sir. Can I ask?
Sure.
Madam, I have two questions. The first question is, what happens when an object goes inside black hole, and is black hole way to another universe like that?
What if object goes inside the black hole?
Yes, madam.
So if it goes inside the black hole, there is no way you can get any information out of it, because as you all know that if it is going beyond the event horizon, nothing comes out. So what we are talking about is always above the event horizon. So the information we are getting is the how the effect of gravity is in the space-time around those black holes, but then the light is coming beyond the event horizon. So nothing can be observed below the event horizon. So I'm not sure what exactly you mean by what if something goes inside the black hole. So can you really make it clearer? What exactly is your question in that context?
And one question I have.
Mhm.
The star survives if nuclear fission force is equal to gravitational force.
Mm-hmm.
What happens during supernova that the star bursts?
Mm. So when there is a supernova explosion, it's sort of a runaway process. So what it actually does is there's explosion of the outer layers of the star, and what remains is the collapsed star, which is undergoing that implosion process. And that compact object, which is resultant out of this supernova explosion, because outer layers of the gas is already expelled in the atmosphere or the universe. So it undergoes that implosion process. That implosion can result into a black hole or a neutron star system. And if it's a very it's really massive star, which undergoes this supernova explosion, then the end product is like a massive black hole. But if you are talking about like 2 to 3 solar mass system which has undergone a supernova explosion, then the remaining, the collapsed star, which is the end product of the star life, will be a neutron star. So this is like a fate of the star being decided.
That means after supernova explosion, the gravitational force is dominating than the nuclear fission force.
When you have this neutron star and a black hole star, a black hole being formed, it's basically known as collapsed stars, and these are dead stars by name. When we say dead stars, there is no nuclear fusion reaction being going on in these systems.
Okay, that means gravity.
So it's just the gravity. That's why they are called dead stars or collapsed stars. Because
Okay, that means gravitational force becomes extremely high.
yes, that's why they are strong gravity objects.
And during supernova explosion, that means outer layer of the star means breaks.
Yeah, it just explodes, and then the outer layers are being expelled out, and then the implosion is the end product of the star. And then because now there's no nuclear fuel to sustain its own life, so what actually sustains these collapsed stars? So for example, in the black hole, these are really collapsed stars, but then in the case of neutron stars, there is something known as degeneracy pressure. So this is pressure due to the electrons in the Fermi system, which exist in these systems at the core of these neutron stars, which basically sustains itself or sustains some sort of pressure to not behave like black holes.
And means at particular time the supernova occurs. Means why at particular time it occurs?
I mean, again, nobody knows exactly the time when the star will explode, because it's basically dependent upon the composition of the star and how much is the nuclear fusion reaction and so on. So it's difficult to really say that when a next supernova explosion can happen, and if it happens in our galaxy or not is a different question. So one cannot really determine the time scale of supernova explosion, but it's just that the process is depletion of the nuclear fuel.
Okay. And
Okay,
this question.
Dr. Kamal Jyoti, let us move on to the other questions also
Okay,
by
sir.
the others. So there is a question from the YouTube link. So MA James is asking, ma'am, what happening to a star when it get old? So when a star gets old, what happens?
So, I mean, aging of the star is again, it can lead to the changes in the composition of the star, because we are talking about again the nuclear fusion reactions here. So, I mean, as it goes older, becomes older, as you saw in the very first or second slide in my presentation, we show different phases of the star cycle. So it can undergo a different phase, which can be a supergiant phase or red giant phase based upon the mass of the star. If it's sun-like star, it can go a red giant phase, and if it's a very massive star, it can go a supergiant phase, and so on. So basically, that is the evolution cycle of your star. So after that, once that phase when it becomes extremely bright, because of the fusion reactions and the radiation pressure being created due to these nuclear fusion reactions, it can become extremely bright objects in the sky. And later on, if that nuclear field is completely depleted from these systems, then we can have those explosion reactions which can lead to the end of this cycle of the star. So I hope that makes it clearer.
Okay. Thank you. And there is the Abhinav is asking, ma'am, what is gravitational lensing?
So if you remember, when I asked the question in that image, like when can you hunt a black hole, then some of the audience members replied that you can measure the effect of the bending of your uh, light around these black holes and so on, which is something similar to known as gravitational lensing. Because these are strong gravity objects, they can have a tendency to bend light, and that bending of light is, if it's coming from the source is galaxies and it's a supermassive black hole, then you can also get the information about the redshift and the galaxies by understanding the gravitational lensing. So it's basically the bending of light coming from the distant galaxies due to these strong gravity objects.
Thank you. And Shailendra is asking, ma'am, why Dirac and Einstein do not believe the existence of mathematical black hole?
What do you mean by mathematical black hole?
Shailendra, if you are there, you may unmute and clarify your question, please. Okay. In the meantime, let's move on to the next question. Arup is asking how a black hole is detected and does it emit any light?
So, black holes, as the name suggests, they do not have their own light because they do not have any source of light in them. What we observe is indirect ways of detecting black holes. One was like detecting in an X-ray band by studying these X-ray binary systems. Second is now we also have gravitational wave detectors, which can basically, if there is a merging effect of like two black holes or a black hole neutron star system merging together, they can distort the space-time curve. And if you can measure the distortion, the degree of distortion of those space-time in form of gravitational wave detection, so you can, with the gravitational wave detectors, you can again measure the presence of that strong gravity objects in the universe. So these are different ways by which you can hunt for those black holes. There are other ways also in which you can basically detect the presence of a black hole in other wave bands, but this is a few of them by which you can really see kind of detect the presence of a black hole. But because black hole are black by name, but they can be bright because of accretion processes, and that accretion processes is one indirect way to hunt for black holes.
Yeah. Aru, can we take two more questions because there are a lot of them?
Sure, no problem.
Okay. So Rishabh is asking, ma'am, will there be any variation in the jets with different orientation of the accretion disk?
Yes, definitely. So, first of all, jets are also not always observed in all systems. These are also transient phenomena. And of course, if your system is edge on or phase on, it can block or like basically favor the emission of the jets. So, to give you a very direct answer to that question, there are not about black hole binary systems, but for example, there are blazars also, which are supermassive black hole systems. You observe strong jets from these systems because you are viewing jets along your line of sight. So again, the inclination of the system have strong effects on those the observation of jets, and they are also function of your accretion rate. So there are different factors which basically influence the formation of jets. So for example, if you talk about black hole systems, in the black hole systems during the hard spectral state, you expect to observe jets in the in the system? Well, when the emission is predominantly from the corona and the accretion disk is receded away from the black hole. But when you are talking about the soft state, there is something known as jet quenching, which means you do not really observe jet during the soft spectral state. So it's not only function of the inclination, but also function of the spectral state of the system. So of course, there is a strong dependency there.
Okay. This Shailendra was asking about mathematical black hole, so he has posted some his questions in the chat box. Ma'am, what will you say about the theories of Dr. Mitra, who don't believe the existence of mathematical black hole, even Dirac and Einstein also? As now theories are coming which violates the universal laws of physics.
I'm not sure of what exactly means violates the. Because until now, our observation, being an observational astronomer, we have not found any evidence which is contradicting the presence of a black hole in the universe. So I'm not sure how the contradiction, because theoretical models may not favor the presence of a black hole, but then being an observational astronomer, I would favor what we observe in the universe. Whether our observations are supporting that theory is an important task or important question. Or so if our observations are favoring the presence of what was proposed in the past by Einstein, if they are favoring, then I would say that there exists black hole. But if there is no signature observationally that contradicts the Einstein theory of relativity, then it's hard to say that they do not exist.
So thank you for the audience to ask your questions. You have been very active throughout. Thank you very much, and I also thank. Yeah.
Sir, in the survey form there is written astronomer's name. What should I write?
I will discuss about that. So please hold on for a few minutes. Okay. So astronomers are those astronomers who have delivered their talks today. Okay. I'm coming to that. So Dr. Aruberi, thank you very much for sparing your precious time and interacting with the audience.
Thank you.
So Sri, can you hand over to Sri? She has some connection issues. So basically, we have reached the end of today's workshop, and formally now is the time for the valedictory session. So I am very glad that all the sessions went smoothly, and I was especially delighted to see the active participation from the audience in both Google Meet and YouTube Live. I apologize for being unable to accommodate all the participants in Google Meet because there is limitation in the total number of participants that can be accommodated in Google Meet. I thank all the speakers of both sessions, Dr. Sujatha Sriramulu, Dr. Shyama Narendranath, Dr. Sonali Sachdeva, and Dr. Aruberi for taking time out from their busy schedule and delivering their talks. I thank the audience for all their questions and the lively interaction with the speakers. I thank the Office for Astronomy Outreach, International Astronomical Union for allowing us to organize the event. I thank the Tezpur University administration in supporting us for organizing the workshop. I thank Professor Parthapratim Sahu sir, Dean School of Engineering, for being a constant source of encouragement. I thank Professor Rajiv Haloy sir and Dr. Dhubajyoti Haloy sir for their support and cooperation in successfully organizing the workshop. I thank Dr. Vijay Krishna Devnath for sparing his valuable time and chairing the first session. I thank all the other Department of Applied Sciences faculty members for their cooperation and support. Last, I thank all the research scholars and the Department of Applied Sciences staff for contributing to the event's success. I especially want to acknowledge the effort of my students, Ms. Sri Bhattacharya, Mr. Arvind Pradhan, and my earlier JRF, Mr. Ankur Nath, who have worked tirelessly to make this event a success. Yes, and there's an announcement for the participants. So, as per mandate of the Meet the IAU Astronomers program of the Office of Astronomy Outreach, I have shared with you the link of a evaluation form, which is named as survey participants. So this survey is regarding the event we had, and your input will directly go to the Office for Astronomy Outreach, International Astronomical Union. So please make sure to fill the survey form. And also regarding your participation certificate, we will share the Google form link to you via email to download your participation certificates very soon. So thanks to all of you very much for making this event a grand success, and I hope to meet you all at another event in the future. Thanks to all. So maybe we can switch on our videos and have some photographs, group photographs. So I request all the participants, if you can, the speakers also, to switch on their camera so that we can have a group photograph. Okay. So, yeah, people are slowly turning on their cameras. Okay, let me have one. So the other participants can also turn on their videos. Okay, so let's take another one. Yeah, thank you very much to all of you, and I hope you have enjoyed and it has been useful to you. So see you next time. Thank you very, very much. And Aruberi, thank you very much. Sonali,
Thank you. Thank you for inviting us. Thanks. Bye.
Bye.
So how much time it will take for getting the certificates?
We'll be sharing the Google form link. You fill up the form, and you will get maybe 100 participants can download at one day, but slowly over. I mean, we will open the link maybe at a time each day. So in a 4 or 5 days, all of you can gradually download your certificates. Maybe we may start from today, or maybe from tomorrow we can start. We'll update you in WhatsApp group.
Sir,
Yes.
I was asking a question just a few minutes back that what should be the astronomer's name? All the four names I can put there.
Yeah, because today's session consisted of 4 IAU astronomers who have delivered their talks.
Okay.
Yeah.
And the participation certificate will be given by mail.
There will be another form. There will be a separate form. This survey of participants will directly go to International Astronomical Union. But regarding your certificate, there will be a separate Google form which will be giving you after some time. Okay.
Okay, sir.
Any other doubts? If not, then all we end the session here. Thank you.
Sir?
Yes.
Sir, I have one doubt, sir.
Yes.
Sir, enter the astronomer's name.
Yes.
My name or so what?
No. The speakers who have it's the speaker's name. The astronomers
Okay,
who
sir.
have given talks today.
Okay, sir. 4 astronomers' names are entered in the.
Yeah.
Okay, yeah. Thank you, sir. Thank you, sir.
Sir, when you will get the link for certificate?
Today we will send you after some time. Okay.
Directly after filling the form, we'll get the certificate, no? First 100 candidates.
Yeah. I think you are already aware of that. Gradually, since the total number of participants are more than 600, it may take a few days for all of the certificates to be distributed. Okay.
Okay, sir.
Thank you.